Good evening and welcome to the Sleepy Scientist. This is your time to unwind, to let the day drift quietly behind you as we journey together through the calm and endless dark of space. Tonight's story belongs to a giant, a world so immense it could swallow more than 1,000 Earths and still have room for dessert. This is Jupiter, the king of planets. Before we begin, I'd love to know, where in the world are you watching from tonight? There's something comforting in knowing that somewhere out there, thousands of us are looking up at the same sky. If you enjoy these peaceful explorations of science, please do give the video a like and subscribe to the channel. And to those already part of this sleepy community, thank you so much for being here. Don't forget to click the little notification bell so you won't miss the next quiet adventure among the stars. I always hope these videos help you relax, but if this one happens to be too interesting and keeps you awake, well, at least you'll fall asleep a little wiser. Now, as the stars begin to blur and the mind settles, let's follow the soft glow of a distant world, a planet of storms, light and mystery. What truly makes Jupiter the king of planets? In the beginning there was dust, fine cold grains swirling in the newborn sun's faint light. Within a few million years, that dust gathered into worlds. But one of them grew faster, hungrier, more powerful than the rest. Jupiter. It was the first to form, and by doing so it reshaped everything that followed. Its immense gravity sculpted the solar system, hurling some worlds inward, flinging others out, and quietly deciding which would survive. Every small planet and wandering comet has, in some way, felt its pull. Yet this giant, for all its power, has no solid ground. What we call its surface is only a sea of clouds, stacked in bands of cream and ochre, striped by winds that race faster than any storm on Earth. Beneath them lies a world of pressure and heat so great that hydrogen itself turns metallic, forging a hidden ocean of liquid metal that glows faintly in the dark. Jupiter is not only a planet, it's a cosmic archive. Its chemistry preserves the earliest whispers of the solar system's birth. Its storms record the restless energy of a world that never truly sleeps. Its magnetic field stretches so far it could engulf the sun itself, wrapping space in invisible ribbons of light and radiation. And around it orbits a miniature solar system of its own. Dozens of moons, each a world with a story. Volcanic Io, icy Europa, vast Ganymede, and ancient Callisto. Together, they dance in rhythms of gravity and time, bound by the pull of their colossal parent. This journey will take us through all of it, from the swirling birth of the planet to the whispering edges of its magnetosphere, where charged particles paint the night with auroras brighter than any seen on Earth. So let's drift closer now, slowly, through the dark. The king of planets awaits, turning endlessly beneath the quiet light of the sun. Long before Earth ever formed, when the sun was still a young and temperamental star, a cloud of dust and gas circled it like a soft spinning fog. Within that haze lay the ingredients for everything to come. Ice, rock, and the simplest atoms that the universe could make. But something extraordinary happened in one region of that vast disk. Matter began to gather faster, clumping together with such greed that it soon became the largest planet in the solar system. Jupiter was born from gravity's hunger. To understand how such a giant came to be, scientists have proposed two main stories. The first is called core accretion, the idea that Jupiter began as a solid embryo, a rocky, icy core that grew by attracting nearby debris. Picture it like a snowball rolling downhill but in space. Every pebble, every dust grain it met was pulled in by gravity, and the snowball swelled. Once this core reached a critical size, around 10 times the mass of Earth, it became powerful enough to start capturing the surrounding hydrogen and helium gas before the newborn sun could blow that gas away. What began as a frozen pebble collector turned into a world wrapped in the lightest elements of the cosmos. The second idea, known as disk instability, paints a different picture. Instead of slow, steady growth, it imagines that Jupiter was born in a kind of cosmic landslide. The disk itself became so massive in certain regions that gravity caused it to collapse directly, forming a giant planet in one sweeping moment. This would explain how Jupiter could form so quickly. Within just a few million years, a blink in cosmic time, before the young sun's radiation stripped the disk of its gas. In truth, reality may be a blend of both ideas, a solid seed forming first, followed by a rapid inflow of gas aided by the unstable, turbulent disk around it. Timing was everything. Jupiter had to form early, while there was still enough gas left in the solar nursery to build its immense atmosphere. Most of the disk's gas was gone within about 10 million years, so Jupiter's growth had to be a race against evaporation. If it had waited too long, it might have ended up as a smaller, Neptune-like world. But it won that race spectacularly, swelling into a planet so large that it holds over twice the mass of all the other planets combined. The composition of Jupiter's atmosphere offers quiet clues to its beginnings. It's made mostly of hydrogen and helium, the same ingredients as the Sun, but with higher levels of heavier elements like carbon, nitrogen and sulfur. That enrichment tells us Jupiter's building blocks weren't just simple gas. They included icy planetesimals, perhaps comets and frost-coated rocks, drifting through the cold outer regions of the protoplanetary disk. These icy fragments likely carried volatile molecules, ammonia, methane and water, into the growing planet, locking away the fingerprints of the early solar system. In a way, Jupiter is a time capsule, a planet-sized archive of what the universe looked like 4.5 billion years ago. As its mass grew, something remarkable happened, a runaway effect. The more material Jupiter gained, the stronger its gravity became, and the more gas it could attract. Growth fed on itself until the process spiraled out of control, pulling in vast amounts of hydrogen and helium. This tipping point is what turned Jupiter from a supersized Earth into a gas giant. Past that threshold, adding more mass didn't make it much bigger, it simply made it denser, compressing its gases under enormous pressure. That's why Jupiter is often called the solar system's heavyweight champion, even though its radius is not dramatically larger than that of Saturn. It is a planet not of bulk alone, but of gravity's deep persistence. There's a popular myth that Jupiter is a failed star. It's easy to see why people say that. After all, it's made mostly of the same gases as the Sun. But the truth is more nuanced. For a planet to ignite fusion, to truly become a star, it needs to be roughly 80 times more massive than Jupiter. Only then would the pressure and temperature at its core be high enough to start fusing hydrogen into helium, releasing the steady light of a sun. Jupiter falls far short of that mark. It doesn't burn, it glows faintly from residual heat left over from its formation. In the quiet cold of space, that warmth is a soft echo of the moment it was born, when compression and collapse filled it with energy. So rather than a failed star, Jupiter is better thought of as the closest thing nature allows to a star without fire. Its presence reshaped everything around it. The newborn giant stirred the disk, scattering debris and sending shock waves through the early solar system. Some of those disturbances helped clear the inner regions of excess material, allowing smaller rocky worlds like Earth and Mars to form safely within. Others flung comets and icy bodies outward, seeding the outer regions that would become the Kuiper Belt and Oort cloud. In that sense, Jupiter didn't just form, it acted as a sculptor, shaping the structure of the solar system we know today. Even now, Jupiter continues to whisper stories of its origin through its gravity, chemistry, and motion. When spacecraft like Juno orbit it, they measure subtle variations in its gravitational field, ripples that tell scientists about its inner layers and the relics of that long-ago formation. Beneath its churning clouds lies a core that may not be solid at all, but a diffuse blend of rock, metal, and hydrogen blurred together under crushing pressure. It is as though Jupiter remembers how it formed, but only in dreams. Imagine it then. Billions of tons of dust and ice drawn inward by invisible hands, spiraling into a deepening gravity well. Heat builds, pressure mounts. At last, a world is born, not in a blaze of fusion, but in the slow, relentless embrace of gravity. In the heart of a cosmic storm of creation, Jupiter took shape, a giant not of light, but of weight. And from that moment on, the solar system would never be the same. Dust and ice became order, drawn into the orbit of a swelling king. The young sun's winds blew across its face, but could not strip away its crown. Jupiter's birth was not just the making of a planet, it was the start of a balance, a harmony between creation and control. In the darkness of the ancient nebula, as the last tendrils of gas drifted away, one world stood vast and new, its gravity humming through the silence, its clouds still forming from the breath of a collapsing sky. The king of planets had arrived, and the universe for a moment held its breath. Jupiter is not just another planet in orbit around the Sun. It's the solar system's quiet choreographer, its gravitational rhythm keeping everything else roughly in line. If the Sun is the conductor of the cosmic orchestra, Jupiter is the booming drum in the back setting the tempo. Its mass, more than twice that of all the other planets combined, bends the paths of comets, shapes the asteroid belt, and even protects the inner planets from wandering debris, most of the time anyway. Its gravity reaches far beyond its own orbit, subtly influencing the shape and safety of our entire celestial neighbourhood. When Jupiter first formed, its gravitational pull was immense enough to rearrange the landscape of the early solar system. Vast swarms of icy rocks and planetesimals were flung outward, sent drifting to the edges where they became the raw material of distant regions like the Kuiper Belt. Others were drawn inward and swallowed by the growing planet or collided with the inner worlds, delivering both destruction and water. Even now, billions of years later, Jupiter's presence still echoes in the motion of countless smaller bodies. Nothing in the solar system moves entirely free of its invisible tug. One of Jupiter's most famous roles is that of the so-called cosmic shield. It's often said that without Jupiter, Earth might be bombarded by far more comets and asteroids than it is today. There's truth in that idea, but it's a bit more complicated than a simple tale of a guardian planet. Jupiter's gravity is powerful but impartial. It doesn't care where objects end up, only that they move. Sometimes it deflects dangerous comets away from the inner planets, tossing them harmlessly into distant orbits. Other times, it can steer them inward, putting them on a direct path toward Earth. It's a cosmic paradox. The same planet that has likely saved our world many times over may also have caused some of its greatest catastrophes. Jupiter is both shield and slingshot, protector and potential troublemaker. It's like a benevolent bouncer who occasionally hurls guests back toward the dance floor instead of out the door. Still, on balance, its presence has reduced the overall number of devastating impacts over the solar system's history. Without its gravitational vigilance, the quiet stability that allowed life to flourish on Earth might never have been possible. Nowhere is Jupiter's shaping power more elegantly displayed than in the asteroid belt between Mars and itself. You might picture the asteroid belt as a dense, chaotic swarm of rocks endlessly colliding, but in truth, it's more like a vast desert sprinkled with scattered boulders. Jupiter's gravity is the reason for that sparseness. The planet's influence reaches across hundreds of millions of kilometers, creating regions of stability and instability that dictate where asteroids can and cannot survive. Within the belt, there are certain places where an asteroid's orbital period forms a simple ratio with Jupiter's. Say, it orbits the Sun exactly 3 times for every 1 orbit of Jupiter, or 5 times for every 2. These are known as orbital resonances, and while the math may sound harmless, the result is anything but. Each time an asteroid in one of these resonances swings around the Sun, it feels a small tug from Jupiter in the same direction. Over millions of years, those tiny nudges add up, amplifying the asteroid's orbit until it's pushed completely out of the region. The result is a series of empty zones within the asteroid belt known as the Kirkwood Gaps. If you could graph the distribution of asteroids by distance from the Sun, you'd see deep troughs where these resonances clear the space like grooves in a record. Jupiter's steady rhythm writes its signature into the solar system itself, an unseen hand carving order into the chaos of drifting stone. But Jupiter doesn't just scatter, it also gathers. On either side of its orbit, 60 degrees ahead and 60 degrees behind, lie 2 enormous groups of asteroids known as the Trojan swarms. These are not random clumps but stable pockets, locked in step with Jupiter's motion by gravity's delicate balance. At these points, called Lagrange points, the gravitational pull of Jupiter and the Sun combine in such a way that small objects can remain parked indefinitely, moving along with the planet as it travels around the Sun. The result is a cosmic convoy, 2 vast flocks of asteroids following their king, like banners fluttering in procession. The leading group is named after Greek heroes, the trailing one after Trojans, though over time astronomers have mixed the names so freely that both camps now host an amusing jumble of mythological characters. Some of these asteroids are large enough to be worlds in their own right, complete with moons of their own, while others are little more than drifting rubble. Together they form a kind of celestial archive, preserving the conditions of the early solar system in orbits that have remained undisturbed for billions of years. These Trojan asteroids are a clue to Jupiter's past migrations. Early in the solar system's history, Jupiter didn't necessarily stay where it is today. Theories like the Grand Tack model suggest that the planet may have moved inward toward the Sun before reversing course and migrating back out. During that wandering, it would have captured material from different regions, sweeping up icy bodies and rocky fragments alike. The Trojans may be relics of that migration, ancient travellers carried along by Jupiter's gravitational tides. In studying them, scientists hope to read the diary of the solar system's turbulent youth. Beyond the asteroid belt and Trojans, Jupiter's reach continues into the outer darkness, shaping the paths of comets and dwarf planets alike. Long-period comets that visit the inner solar system often owe their journeys to Jupiter's distant influence, their orbits nudged into elongated ellipses that bring them inward to flash briefly across our skies before being flung back into the cold. Even Neptune and Uranus may owe part of their current arrangement to the early gravitational games Jupiter played. It is, quite literally, the reason the solar system looks the way it does. Jupiter's balancing act, sometimes protective, sometimes perilous, has shaped the very conditions that allowed Earth to remain habitable. Without it, the asteroid belt might have formed into another planet, perhaps destabilizing the inner orbits. With it, the solar system remains dynamic yet orderly, a blend of chaos and structure that endures through billions of years. Jupiter doesn't simply orbit the Sun, it orchestrates the dance of countless smaller worlds, If you could somehow step outside the solar system and watch it unfold from afar, you would see Jupiter's influence everywhere. Its gravity pulls comets into curved arcs, sculpts the belts of debris, and holds the Trojan swarms like ornaments on an invisible thread. Every small motion, every shifting orbit is part of the slow cosmic choreography written by this immense world. And yet, for all its might, Jupiter remains a subtle artist. It doesn't announce itself with fire or fusion, but with balance and quiet power. Its gravitational reach is vast, but its touch is measured, sculpting, adjusting, guiding. It is both guardian and gardener, ensuring that the solar system's garden of worlds remains diverse and enduring. Far from being just a massive ball of gas, Jupiter is a cosmic architect, shaping the solar system's rhythm with every orbit. The asteroids that cluster and the comets that swing past owe their paths to its steady hand. The king does not rule through force alone, but through harmony, the gravity of presence. And as it circles the sun, vast and unhurried, the planet's gravity continues to write invisible lines through space. Lines that guide, protect, and sometimes surprise. From the smallest pebble in the asteroid belt to the largest world beyond Neptune, all of them move in some way to Jupiter's silent command. Now follow that pull a little closer, past the orbits and the Trojan flocks, toward the planet itself, where those unseen forces become visible, painted across a surface of clouds and colour. Seen through a telescope, Jupiter looks like a painting in motion, ribbons of cream, caramel, ochre, and rust swirling across a vast canvas of clouds. No other planet wears such complex colours. From a distance, it appears almost calm, like the soft marbling of coffee and cream. But those serene bands are anything but still. Each hue tells a story of chemistry, temperature and motion, written in layers of cloud hundreds of kilometres deep. To understand those colours, we first need to imagine Jupiter's atmosphere not as a single blanket, but as a towering layer cake of gases and ice. At the very top, high above the bulk of the atmosphere, sunlight filters through a haze of ammonia crystals. This layer forms delicate white clouds that drift across the highest regions, reflecting sunlight and giving Jupiter its bright, creamy tone. Beneath that, about 80 to 100 kilometers down, conditions grow warmer and more exotic. Here, ammonia gas reacts with hydrogen sulfide to form ammonium hydrosulfide, a compound that condenses into reddish or brownish clouds. Deeper still, farther than any visible light can easily reach, lie the water clouds, enormous, dense structures of frozen droplets and vapour that behave more like thunderstorms than wisps of mist. These three main decks, ammonia ice, ammonium hydrosulfide and water, form the scaffolding of Jupiter's atmosphere. Together they paint the planet's face. But the real artistry comes from the molecules that give those clouds their tints. Scientists call them chromophores, tiny compounds that absorb certain colours of light while reflecting others. Their exact identities remain partly mysterious. Some may be complex sulfur or phosphorus-bearing molecules. Others could be the chemical products of sunlight breaking down ammonia or other gases in the upper atmosphere. What we do know is that these pigments are created and destroyed by both chemistry and weather. As gases rise from the deeper, hotter layers below and meet ultraviolet sunlight from above, they react to form new compounds, tinting the upper clouds in soft yellows, golds, and brick reds. The process is slow but constant, Jupiter's own version of aging varnish on a masterpiece. The bands we see, the alternating light zones and dark belts, are not painted stripes at all, but vast, circulating rivers of air that flow in opposite directions. The pale zones are regions of rising motion, where material from below pushes upward, cooling as it ascends and forming bright ammonia clouds high in the atmosphere. The darker belts are sinking regions where air descends, warms, and clears away the upper clouds, revealing deeper, darker layers rich in ammonium hydrosulfide and other coloured compounds. It's as though the planet is breathing, light rising, dark falling, an endless inhale and exhale of gas and chemistry. These belts and zones are not random. They are the outward signs of Jupiter's immense internal heat and its rapid rotation, which together drive fierce jet streams that circle the planet. The interaction of these winds and temperatures determines how deep each band reaches, what chemicals it exposes, and therefore what colour it takes on. Where gases rise, they cool and condense into pale clouds. Where they sink, they dry out and darken. Seen from afar, this pattern turns Jupiter into a colossal thermal fingerprint, each band a unique combination of temperature, altitude, and chemical composition. Sunlight also plays its part. Even though Jupiter receives only about 4% as much sunlight as Earth, that light still shapes the atmosphere. Ultraviolet radiation breaks apart molecules like ammonia and methane, creating a cascade of chemical reactions that produce the chromophores responsible for the planet's tan and red hues. In the uppermost layers, high-energy particles from Jupiter's intense magnetic field join the dance, striking atoms and triggering new reactions. Over time, this slow bombardment alters the colours we see, shifting them subtly from year to year, sometimes brightening, sometimes fading, as if the planet is changing moods. If we could stand within Jupiter's clouds, an impossible wish since the pressure and temperature would crush and dissolve any visitor long before reaching the deeper levels, the scene would be extraordinary. At the top, the light would be dim and diffuse, filtered through layers of haze. Wisps of ammonia snow would drift like powdered sugar in the thin air. Deeper down, the sky would turn ochre, then burnished copper as the ammonium hydrosulfide clouds came into view. Lightning might flash in the distance, illuminating the outlines of vast convective towers rising tens of kilometers high. Each layer would have its own climate, its own color palette, a world within a world. Even from afar, telescopes can glimpse this dynamic beauty. High-altitude clouds cast shadows on lower layers, creating subtle textures. Long plumes of white appear where updrafts disturb the usual flow, and dark streaks mark places where descending air clears the haze. Instruments aboard spacecraft like Juno can see beyond visible light, peering into the infrared to measure temperature and composition, confirming that these color differences are more than skin deep. They reveal structure, real weather patterns rising and falling in slow, endless cycles. For all their grandeur, these colors are delicate, constantly changing with the planet's shifting chemistry and sunlight. The Great Red Spot, for instance, owes its distinctive hue to similar reactions between sunlight and the gases churned up from below, yet even its color varies from deep brick to salmon pink, suggesting that the mix of molecules in Jupiter's atmosphere changes over time. In the grand scheme, the planet is not static but evolving, a living artwork being continually repainted by physics. Each belt and zone also has its own temperature and depth. The bright equatorial zone, for instance, is relatively cool, while the darker belts are warmer and thinner. In some places, bright plumes of ammonia-rich air rise high, spilling into neighbouring regions and forming delicate lace-like edges. To the human eye, these contrasts create the illusion of three-dimensional texture, the sense that Jupiter's face is carved in motion. In truth, it's a projection of energy and chemistry, a map of invisible convection currents made visible through colour. And then there are the hazes, those thin veils of particles that float above the main clouds like a misty film. They scatter sunlight, softening the boundaries between belts and zones, giving Jupiter its familiar blurred beauty. These hazes form when sunlight breaks apart molecules in the upper atmosphere, allowing their fragments to recombine into complex sticky clusters that drift downward like cosmic pollen. Over time, they build up into sheets that tint the light and help maintain the planet's overall palette. The result is a world that never looks quite the same twice. Amateur astronomers often notice subtle changes from year to year, a belt that fades, a zone that brightens, new spots or plumes appearing in places that were once calm. Jupiter's clouds are dynamic, reshaping themselves on timescales of weeks or months. Beneath their tranquil appearance lies a restless system, where heat, sunlight and chemistry weave together in ever-changing patterns. It's humbling to realize that the planet's beauty is not painted on. It's born from constant motion and transformation. The colors of Jupiter are the visible signature of invisible forces, the soft glow of physics at work in a realm too vast and deep for any human eye to truly comprehend. Look long enough at those swirling bands, and they begin to feel almost alive. Cream-coloured zones stretching like strands of silk, cinnamon belts rolling and folding over one another, faint mists draping the horizon in a hazy veil. A world of cloud and colour, forever stirring, forever remade. And yet, for all its chaos, Jupiter's face remains balanced and rhythmic, each stripe holding its place in the great atmospheric dance. From above, it's as if the planet has found harmony in turbulence. The colours are not just decoration, they are the language of its weather, the poetry of chemistry written in wind. Now, as we leave the stillness of observation, turn to the motion itself, the winds that draw these stripes, and the forces that keep them flowing endlessly around the king of planets. From a distance, Jupiter's stripes look almost painted on, as if some cosmic artist dragged a brush across the planet's surface and left behind perfect, endless ribbons of cream and amber. But those bands aren't painted. They're winds, flowing with a precision and ferocity unmatched anywhere else in the solar system. The entire planet is wrapped in a symphony of jet streams, each one moving in opposite directions to its neighbours, circling the globe at hundreds of kilometres per hour. If you could somehow float above the clouds and watch the atmosphere move, you'd see the whole planet playing an intricate silent song of motion. Each band a note, each wind a melody in a rhythm older than time itself. Jupiter's rotation is the key to its striped perfection. The planet spins once every 10 hours, even though it's more than 100 times wider than Earth. That means points near its equator move at incredible speeds, over 40,000 kilometers per hour. Such rapid rotation twists and stretches the atmosphere, breaking large currents into narrow jets that wrap around the planet from east to west. Each jet becomes the boundary between light zones and dark belts, separating regions of rising and sinking air. The result is a world that looks like it's been carefully layered by nature's own centrifugal hand. These alternating bands of wind, some eastward, some westward, form what scientists call jet streams. Earth has a few of them, but Jupiter has more than a dozen, all far stronger and deeper. The reason lies partly in the planet's size and partly in the way rotation interacts with convection. On Jupiter, hot gas from the interior rises while cooler gas sinks. But because the planet is spinning so fast, those vertical movements are constantly deflected sideways by a force known as the Coriolis effect. It's the same phenomenon that helps twist hurricanes on Earth, but on Jupiter, it shapes the entire global weather system. Rising air veers one way, sinking air another, until the whole atmosphere organizes itself into alternating lanes of motion, a planetary racetrack in permanent flow. The light-coloured zones are where air rises, cools and condenses into bright ammonia clouds. These are the gentler, calmer regions. The darker belts, on the other hand, are where air sinks, dries and warms, creating clear patches that reveal deeper, darker layers. Between them, fierce shear zones form, thin but powerful boundaries where neighbouring jet streams rub against each other, generating turbulence, waves, and sometimes vast storms. It's along these shearing edges that many of Jupiter's ovals and vortices are born, like eddies forming where two ocean currents meet. Scientists describe these flows using terms borrowed from fluid dynamics: barotropic and baroclinic. In a barotropic flow, the winds move uniformly with depth, like a solid sheet sliding over itself. In a baroclinic flow, temperature and density vary with height, causing layers to slip and twist relative to one another. On Earth, most of our weather is baroclinic. Fronts and storms form where warm and cold air masses collide. But on Jupiter, much of the atmosphere behaves more like a barotropic fluid, with its powerful winds maintaining their speed and direction deep below the visible clouds. It's as if the planet's weather is not a surface phenomenon but a three-dimensional current, an ocean of air that stretches down thousands of kilometers. For a long time, scientists didn't know how deep these jet streams actually went. Were the stripes just a thin pattern painted on the upper atmosphere, or did they extend far below, rooted in the planet's mysterious interior? The answer came from the Juno spacecraft, which began orbiting Jupiter in 2016. By measuring subtle variations in the planet's gravity field as it flew past, Juno could sense how mass moved beneath the clouds. The results were astonishing. Jupiter's jet streams extend roughly 3,000 kilometers below the surface, far deeper than anyone expected. That's about 300 times the depth of Earth's oceans. These are not just winds, they're colossal systems, penetrating into layers where the pressure is so great that hydrogen begins to act more like a liquid metal than a gas. This deep circulation hints at how Jupiter's interior transfers heat. The planet radiates more energy than it receives from the Sun, powered by slow contraction and leftover heat from its formation. That internal warmth bubbles upward, setting the entire atmosphere in motion. As the heat rises, the planet's rotation twists it into bands, which then interact and stabilize into the striped pattern we see today. It's a dance between energy and spin, gravity pulling inward, heat pushing outward, and rotation shaping the flow into ordered chaos. Each band moves at astonishing speed. Near the equator, eastward winds can reach over 500 kilometers per hour. At higher latitudes, westward jets take over, reversing direction, but maintaining roughly the same strength. These alternating streams remain stable for centuries, locked in place by the planet's rotation. The boundaries between them are not fixed walls, but shifting regions where turbulence thrives. Here, smaller storms can merge, stretch, or tear apart, feeding energy into the system like drummers keeping rhythm in a never-ending song. From afar, the effect is mesmerizing. The pale zones look like sheets of silk, flowing gently in one direction, while the darker belts move the other way, their edges curling and twisting like smoke caught between opposing breezes. Tiny white ovals, storms the size of Earth, drift along these borderlines, spinning gently in the turbulent air. Each one is born from the friction between bands, living for weeks or even years before fading back into the surrounding flow. In the deeper layers, unseen by any camera, these same patterns continue, possibly merging into vast, slow-moving currents that encircle the entire planet. It's a level of organization that seems almost musical. Imagine Jupiter as a cosmic symphony, each jet stream a note in a vast chord, each storm a brief solo, and the belts and zones the repeating rhythm that ties it all together. The planet is not chaotic. It's orchestrated. Its stripes are the visible notes of an invisible score written by physics. And though Jupiter's atmosphere may look timeless, it is always in motion. New storms form, old ones vanish, and the balance between belts and zones shifts ever so slightly. The planet's rapid spin keeps everything synchronized, but nothing is truly still. Even now, scientists continue to study how these jets stay stable for so long, why the same stripes have persisted for centuries while smaller details change from year to year. Some models suggest that the deep winds tap into the planet's internal heat, creating a feedback loop that sustains them indefinitely. Others think magnetic fields deep inside the planet help anchor the flow, acting as invisible rails beneath the storm. Whatever the mechanism, the result is hypnotic, a world whose surface is pure motion, structured yet unpredictable, violent yet graceful. Jupiter's stripes are more than weather. They are the planet's heartbeat, pulsing endlessly beneath the faint sunlight of the outer solar system. Look closely and you can almost hear it, the low rolling rhythm of hydrogen and heat, the harmony of gas and gravity. The belts and zones move in counterpoint, the jet streams hum in harmony, and somewhere within that ceaseless flow, a single note swells louder than the rest. It is the voice of a storm that has raged for centuries, vast and defiant, turning endlessly in Jupiter's southern hemisphere, the Great Red Spot. For centuries, the Great Red Spot has turned slowly in Jupiter's southern hemisphere, a storm so enormous it could once have swallowed 3 Earths whole. It's the most famous weather system in the solar system, a vast churning oval that has outlived entire human civilizations. Telescopes in the 1700s first recorded it, but by then it was already ancient, spinning endlessly in the deep ochre atmosphere of the King of Planets. At its heart, the Great Red Spot is an anticyclone, a high-pressure system rotating counterclockwise in the southern hemisphere, opposite to hurricanes on Earth. Instead of drawing air inward, it pushes outward and upward, creating a towering dome of swirling clouds. The storm sits between 2 of Jupiter's strongest jet streams, one moving eastward above it, the other westward below. These opposing winds stretch the storm into its familiar oval shape, like a spinning drop of paint caught between 2 conveyor belts. Despite the chaos around it, the Great Red Spot endures, feeding on the very turbulence that surrounds it. This endurance is one of its great mysteries. Most storms on Earth last days, maybe weeks, before losing energy. But the Great Red Spot has raged for at least 350 years, and possibly far longer. The secret lies in Jupiter's lack of solid ground. On Earth, hurricanes weaken when they hit land, cut off from their source of warm, moist air. Jupiter has no such surface to interfere. The storm can spin freely, drawing energy from the planet's internal heat and from the endless shear between the surrounding jet streams. Like an eddy in an infinite river, it is sustained by motion itself. Its rotation is fierce. Winds circle the edge of the storm at speeds up to 430 kilometers per hour, though the center remains surprisingly calm, a wide eye of high, cold cloud tops floating miles above the surrounding atmosphere. Beneath those clouds lies a layered column that likely extends hundreds of kilometers deep, perhaps rooted in regions where hydrogen behaves more like liquid than gas. The upper layers, visible to telescopes, are only the crown of a much deeper phenomenon, one that may reach into the very weather engine of the planet. Yet even this ancient tempest is changing. Over the last century, observers have watched it slowly shrink, its once sprawling diameter now only about half what it was in the 1800s. From a colossal 3 Earths across to just a little more than 1, the storm is gradually tightening its grip, becoming smaller and rounder. The cause isn't fully understood. It could be losing energy to nearby jet streams, or simply evolving into a more compact, efficient vortex. Whatever the reason, the change is gentle, measured in decades rather than days. The Great Red Spot is not dying, it's adapting, reshaping itself in the slow rhythm of planetary time. Its colour, too, shifts with the years. Some generations have seen it a deep blood-red oval, others a pale salmon or faded peach. Scientists think this colour comes from chemicals in the upper atmosphere reacting with sunlight, perhaps sulfur or phosphorus compounds formed when ultraviolet light breaks down ammonia and other gases. Those reactions create reddish pigments that coat the high-altitude clouds. As the chemistry of Jupiter's atmosphere changes, or as the storm lifts or lowers its top layers, the hue changes too. It's as though the storm keeps repainting itself, sometimes bold and fiery, sometimes muted and weary. Through spacecraft observations and telescopic monitoring, scientists have learned that the Great Red Spot is not a flat disk, but a towering structure. The cloud tops rise more than 8 kilometers higher than the surrounding regions. Inside, air spirals upward, cools, and spreads outward, creating a bright outer rim that catches sunlight and contrasts sharply with the darker belts around it. The storm's outer edges are chaotic, constantly shedding and reabsorbing smaller vortices. These smaller storms feed into it like tributaries joining a river, replenishing its spin. It's a perfect example of vorticity recycling, where turbulence itself keeps the system alive. Energy doesn't dissipate, it is transferred, reabsorbed and reborn within the swirling architecture of the storm. In the grand scale of Jupiter's weather, the Great Red Spot isn't alone. It's simply the most famous member of a vast family of vortices that populate the planet. Smaller red spots, white ovals, and brown barges form and vanish across the belts, some merging to grow stronger, others torn apart by shear. But the Great Red Spot reigns as the eldest, the survivor. It's the solar system's most patient weather complaint, muttering for centuries without ever running out of breath. If you could drift above it, the view would be breathtaking. Below, a spinning oval the size of a world, its edges streaked with white filaments of cloud torn from nearby jet streams. Inside the oval, reddish hues swirl and fade into subtle gradients, deep rust at the edges, fading to soft peach near the centre. Sunlight glints off the upper clouds, casting delicate shadows across the layers beneath. To the human eye, it might look calm, almost still, but beneath that serenity are winds moving faster than any earthly storm could sustain. The dynamics of the Great Red Spot can even be heard in a sense. When scientists translate atmospheric data into sound, the variations in pressure and speed resemble deep rolling tones, a kind of planetary hum. It's not literal music, but it captures the feeling of rhythm and endurance. The storm is less like a violent outburst and more like a slow, eternal drumbeat in Jupiter's endless symphony of motion. Despite its immensity, the Great Red Spot is fragile compared to the scale of the planet. Jupiter could swallow it a dozen times over and still have room to spare. Yet, in its persistence lies something profound. It reminds us that even in a world of violent forces, stability can emerge, not through stillness, but through balance. The storm survives by interacting with its chaotic surroundings, drawing strength from what would destroy lesser systems. In that sense, it's a living symbol of resilience, an eye of order in a sea of turbulence. As we watch it change year by year, we're seeing not the end of a storm, but a process that mirrors the life of all dynamic systems. Things grow, stabilize, decay, and reform. Perhaps one day, centuries from now, the Great Red Spot will finally fade, leaving behind only a faint trace of its rotation in the planet's deeper winds. But until then, it continues to turn, unhurried, ancient, and vast, like a thought that never quite ends. From the moment telescopes first glimpsed it to the close-up portraits captured by passing spacecraft, the Great Red Spot has been our window into the persistence of chaos. It's both a storm and a story, a reminder that longevity doesn't always come from calm, but from the ability to keep moving with the currents of change. And Jupiter has many such stories to tell, for where one storm leads, others follow, swirling, colliding, and weaving their patterns into the endless dance of clouds that covers the face of the king of planets. Weather on Jupiter is not a passing mood, it's a constant performance. Across its vast cloud-wrapped surface, storms are born, grow, collide, and vanish in a grand cycle of motion and renewal. Every cloud on Jupiter is part of an atmosphere alive with electricity and convection, powered by deep internal heat rather than sunlight. Lightning flashes, wind shears twist, and waves ripple through the planet's endless belts and zones. If Earth's weather feels energetic, Jupiter's is an orchestra tuned to a far greater scale. One of the most striking discoveries about Jupiter's weather came from its lightning. Spacecraft like Voyager, Galileo, and Juno have captured brilliant branching flashes of light, illuminating the tops of clouds thousands of kilometers wide. These bolts can be hundreds of times more powerful than any thunderstorm on Earth, crackling deep within the water clouds far below the visible ammonia haze. Their light can pierce through multiple layers of atmosphere, glowing faintly from within like lanterns under a sea of vapor. Each strike is the result of convection, hot air rising, cool air sinking, water droplets colliding, and static charges building until the atmosphere discharges in blinding electric fury. Unlike Earth, Jupiter's lightning is concentrated near the poles and deep inside the cloud layers, where water exists as both liquid and ice. These regions serve as the dynamo of the planet's weather, fueling vast convective towers that rise through the atmosphere. Imagine an updraft so powerful that it carries water vapor upward for dozens of kilometers before cooling, condensing, and forming towering thunderheads capped by ammonia ice. When those droplets freeze, they release heat, driving the convection even harder, a feedback loop of heat and turbulence that keeps Jupiter's storms alive. Far above these deep lightning factories, the cloud tops display an entire ecosystem of storms. Some are temporary, bright white spots that drift through the belts, compact, oval-shaped storms known as white ovals. Others are darker, brownish features called barges, often found within the planet's belts. White ovals form in regions of high pressure, similar to the Great Red Spot, but they are smaller and shorter-lived. Over time, these ovals can merge, grow stronger, or fade away, part of a continuous cycle of formation and decay. Barges, on the other hand, are lower pressure systems that appear as holes in the cloud decks, giving glimpses into the deeper, darker atmosphere below. They are the quiet inverses of the brighter ovals, complementing Jupiter's weather with subtle contrasts of shadow and light. Sometimes these storms interact in dramatic ways. Two ovals might approach each other, spinning faster as they draw near, and eventually merge into a single, larger vortex. When that happens, the surviving storm often grows stronger, feeding off the combined energy of both parents. The result is an atmosphere where storms behave almost like living organisms, competing, combining, and evolving. These mergers and absorptions are not rare. Jupiter's belts are full of such interactions, creating an ever-shifting mosaic of ovals, streaks, and filaments. Despite the immense violence taking place within its clouds, Jupiter's atmosphere has an underlying structure, a rhythm that keeps chaos in check. The pale zones are areas of relative calm, where air rises gently and forms stable. Bright ammonia clouds, these are the serene bands, wide and luminous, where little turbulence breaks the surface. In contrast, the darker belts are wild, storm-tossed regions of descending air and turbulent motion. Here, powerful winds shear and twist the atmosphere, spawning vortices and waves that propagate across thousands of kilometers. Together, the belts and zones form a planetary pulse, a balance between stillness and storm, between calm breathing and deep convective energy. In some regions, towering plumes erupt like slow-motion fountains. These columns of rising air can reach tens of kilometers high, topped by brilliant white domes that shine even in the dim light so far from the sun. Scientists have compared them to the shape of mushroom clouds, not in violence but in form, where heated material rises, spreads, and cools in graceful, billowing layers. These immense upwellings transport water, ammonia, and other chemicals from deep within the atmosphere to the upper levels, helping to mix and refresh Jupiter's weather. They're vital to the planet's storm ecology, the dynamic balance that allows the system to sustain itself over time. Jupiter's storms also create beautiful wave patterns, long rippling features that can stretch across the planet. These atmospheric waves behave like ripples in a vast fluid ocean, spreading energy from one region to another. Some form at the boundaries between belts and zones, where jet streams move in opposite directions. Others are triggered by convection deep below, rising upward until they manifest as faint curving bands. In some cases, these waves may even influence the timing of major storm outbreaks, creating long-term rhythms that repeat over decades. The colours of Jupiter's storms reflect their altitude and chemistry. Bright white ovals form where ammonia ice clouds reach high altitudes and reflect sunlight, while darker brown or red regions mark areas where the clouds are thinner or mixed with deeper materials. As storms evolve, their colours shift, recording changes in temperature and composition. Observations over decades reveal that Jupiter's entire appearance, its stripes, spots, and plumes, changes subtly over time, as if the planet is breathing in slow motion. The contrast between the calm zones and turbulent belts creates an atmosphere of balance through difference. The zones are vast, slow, and luminous, drifting almost peacefully. The belts, in contrast, are restless, full of hidden lightning, swirling eddies, and rapid convection. Together they maintain equilibrium across the planet. Energy flows upward in the zones and downward in the belts, completing the grand circuit that keeps the atmosphere alive. It's a delicate dance of energy, a planetary heartbeat that never stops. What makes Jupiter's weather even more extraordinary is that it's powered mostly from within. Unlike Earth, where sunlight drives the winds, Jupiter radiates more heat than it receives from the sun. This internal warmth, left over from its formation and from slow gravitational contraction, stirs the deep layers of hydrogen and helium, driving convection from the inside out. Every storm, every bolt of lightning, every swirling oval is a manifestation of that buried heat escaping into space. From orbit, spacecraft have captured lightning flashing through the clouds, illuminating the night side of the planet with momentary brilliance. These flashes appear as tiny sparks on a vast canvas, but each one represents immense energy. An instant of raw power inside a world where storms are the norm, not the exception. The more scientists observe, the clearer it becomes that Jupiter's atmosphere behaves like a living system, endlessly recycling its energy and material through storms that both destroy and renew. There is a rhythm to it all. Storms appear, fade, and reappear in slightly new forms, their life cycles overlapping like the verses of an endless song. Jupiter's weather is never finished. It is always in motion, always revising its own patterns. This ceaseless transformation has continued for billions of years and will continue for billions more. An atmosphere that remembers its past only through the structures it leaves behind. Beneath the swirling colours and endless storms deeper still, the air grows denser, hotter, and stranger. Pressure mounts, hydrogen thickens, and the boundaries between gas and liquid begin to blur. The storms above are only the surface ripples of a much deeper ocean of motion, one that leads into realms where matter itself begins to change. Now it is time to sink beneath the clouds toward that unfamiliar world of metallic winds and hidden heat. Beneath Jupiter's endless clouds, where lightning fades and sunlight can no longer reach, lies a realm of deepening pressure and strangeness. Every kilometre downward is another step into an environment unlike anything found on Earth, a world without surface, without solid ground, where air thickens into liquid and atoms themselves begin to behave differently. The deeper you go, the more the laws of matter seem to bend under the weight of gravity's hand. At first, the descent would take you through layers of familiar gas, mostly hydrogen and helium, the same ingredients that make up stars. But pressure mounts quickly on Jupiter. A few hundred kilometers down, the atmosphere grows so dense that it no longer behaves like a gas at all. Hydrogen molecules, packed shoulder to shoulder, begin to press against one another until the space between them nearly disappears. Temperatures rise to thousands of degrees, and the gas transitions into a hot fluid form, still transparent in parts, but heavy, shimmering, and more like a liquid than an atmosphere. Keep falling, and the transformation becomes even more dramatic. At pressures over 1 million times that of Earth's sea level, hydrogen changes character completely. The electrons that normally orbit hydrogen's protons are forced free, moving through the dense fluid like a metallic sea of charge. Hydrogen, the simplest of all elements, becomes metallic, an electrically conductive liquid that can carry current as easily as copper wire. This extraordinary substance doesn't exist naturally anywhere on Earth. It can only form under the crushing pressure of giant planets or in the hearts of stars. This metallic hydrogen is thought to make up much of Jupiter's interior. It flows like molten metal, glimmering invisibly in the darkness, and may extend for tens of thousands of kilometers toward the core. As it moves, it generates electric currents that give rise to Jupiter's immense magnetic field. The planet, in effect, has an ocean of metal swirling beneath its clouds. It is one of the strangest substances known to science, a liquid metal born not of heat alone, but of sheer pressure. For decades, scientists imagined Jupiter had a distinct solid core, perhaps a dense ball of rock and metal hidden beneath its metallic hydrogen mantle. But more recent data, especially from the Juno spacecraft, suggests something more complex. Rather than a cleanly defined core, Jupiter may have what's called a diluted core, a region where heavy elements are mixed gradually into the surrounding hydrogen instead of forming a sharp boundary. Gravity measurements reveal that the planet's mass is spread in a fuzzy gradient, not neatly layered like an onion. It's as if the planet's interior was stirred at some point in its history, blending rock, ice, and metal into the deep metallic sea. This finding adds new depth to our understanding of Jupiter's formation. Perhaps when it was young, a colossal impact with another protoplanet disrupted its internal structure, scattering the solid core and mixing it throughout the lower layers. Or perhaps the intense convection inside the planet gradually eroded the core over billions of years. Whatever the cause, Jupiter's heart is not a tidy sphere of stone. It's more like a slow, molten storm of heavy elements adrift in a sea of metallic hydrogen. Heat still flows outward from that deep interior, a remnant of Jupiter's birth. The planet radiates more energy into space than it receives from the sun, glowing faintly in infrared light. This warmth comes partly from residual heat, left over from its original collapse, and partly from the slow settling of helium droplets within the planet's interior. As helium separates from hydrogen under immense pressure, it drizzles downward like rain in reverse, releasing gravitational energy as it falls. That steady rain of helium helps power Jupiter's convective motions, and may explain why the planet's atmosphere is slightly depleted in helium near the top. It's literally raining out of the sky, deep into the metallic ocean below. If one could somehow listen to Jupiter, the sound would not be silence. Waves of pressure travel through its interior, resonating like notes within an enormous musical instrument. Scientists can measure these oscillations, called planetary seismology, to infer details about the planet's structure, much like listening to the vibrations of a bell to learn what it's made of. These faint tremors suggest that Jupiter's interior is remarkably fluid and continuous, with no abrupt boundaries. It's a world where density and pressure increase smoothly, where air becomes liquid and liquid becomes metal. The deeper you imagine sinking, the more surreal the environment becomes. The atmosphere darkens to a dim copper glow. Heat rises until it could melt steel. Pressure climbs to levels no material could withstand. There is no floor, no boundary where one could stop. Even the word inside feels inadequate. On Jupiter, everything blends. Gases flow into liquids, liquids into metallic plasma, and somewhere in that continuum lies the planet's elusive core. To describe this descent is to speak of sound and density rather than shape. Pressure increases like a choir swelling in a cathedral made of hydrogen, soft at first, then immense, until every molecule seems to vibrate in unison. The weight of the planet presses inward, but the response is not collapse, it's transformation. Under the strain, hydrogen does not break, it adapts, changing its very nature to bear the load. All the while, the planet's heat and motion continue to churn. Convection carries energy outward, mixing layers and distributing warmth. Even though Jupiter has no solid crust or mantle, it behaves like a dynamic engine, circulating energy from its molten heart to the frigid edge of space. This flow maintains the planet's weather systems, powers its storms, and sustains its magnetic might. Scientists continue to refine models of what happens in these crushing depths, but one truth remains clear. Jupiter is not a static ball of gas. It's an evolving, restless body, alive with internal movement. Its deep layers store more mysteries than the surface could ever reveal. Somewhere below, in the hidden pressure and metallic shimmer, lies the key to the planet's longevity and strength. This is the paradox of Jupiter's interior: immense pressure, unimaginable heat, and yet a kind of harmony. Within that chaos, the planet maintains balance, channeling energy upward in slow, steady waves. Every storm on the surface, every lightning flash and swirling band, ultimately draws its strength from this silent ocean below. And in that deep metallic sea, where pressure becomes current and matter becomes conductor, the story takes another turn. The same flows that sustain the planet's heat also give rise to one of the most powerful magnetic fields in the solar system. A magnetic sea that stretches far into space, invisible yet immense, wrapping Jupiter in its unseen embrace. Deep within Jupiter's hidden layers, where hydrogen flows like molten metal, the planet's greatest invisible force is born. Here, in the metallic heart of the giant, electricity stirs. The combination of metallic hydrogen and rapid rotation turns Jupiter into a colossal dynamo, a natural generator on a planetary scale. Every 10 hours the planet spins once, and with each turn, electric currents swirl through the metallic ocean below the clouds, giving rise to a magnetic field so vast and powerful it would make Earth's look like a child's toy compass. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's at its surface. But strength alone doesn't capture its true grandeur. The field stretches millions of kilometers into space, forming an enormous bubble of magnetism known as the magnetosphere. If it were visible, it would appear as an invisible cloak surrounding the planet, one so large that if it could be seen from Earth, it would shine wider than the full moon. It is, in every sense, the king's invisible cape, majestic, powerful, and very, very large. This immense field is powered by motion deep within Jupiter's interior. Metallic hydrogen, compressed under pressures millions of times greater than those at Earth's surface, conducts electricity like a liquid metal. As the planet spins, these conducting layers move within the magnetic field they themselves generate, reinforcing and sustaining it. It's the same principle that drives Earth's magnetic field, but on Jupiter, the scale is beyond comprehension. The faster spin, the thicker conducting layer, and the enormous volume all conspire to make Jupiter's magnetism one of the most dominant forces in the solar system. But Jupiter's field isn't neat or symmetrical. For many years, scientists imagined it as a simple bar magnet, a tidy north and south pole aligned near the planet's rotation axis. Then came the Juno spacecraft, carrying instruments designed to map the field in exquisite detail. The results were startling. Jupiter's magnetic field is lopsided and patchy, its poles offset and twisted. Near the equator, magnetic loops rise and fall unpredictably, creating regions of intense magnetism interspersed with weaker zones. It's as if the dynamo deep within is not spinning on one perfect axis, but roiling and undulating, like molten metal caught in perpetual motion. The North Pole in particular revealed a strange feature, a cluster of concentrated magnetic spots rather than one clean field line. This great blue spot, a region of particularly strong and complex magnetism, mirrors the irregularities of the planet's internal flow. It's a reminder that Jupiter's heart is not static. It's alive, shifting, and possibly evolving. The planet's magnetic personality is far more intricate than the simple diagrams once drawn in textbooks. The size of Jupiter's magnetosphere defies intuition. On the day side, where the solar wind presses against it, the field is compressed to a boundary about 7 million kilometers from the planet's center. But on the night side, it stretches away in a vast magnetotail, a long tapering stream that extends beyond the orbit of Saturn. This magnetotail acts like a highway for charged particles, funneling energy and plasma across millions of kilometers. In a sense, Jupiter drags its own magnetic shadow through the solar system. Closer in, the magnetic field traps high-energy particles, forming radiation belts far more intense than anything around Earth. These belts are filled with electrons, protons, and ions stripped from Jupiter's volcanic moon Io, which constantly erupts sulfur and oxygen into space. Those particles are caught by Jupiter's magnetic field and accelerated to near-light speeds, creating a lethal environment for spacecraft. It's a region so intense that electronics must be shielded behind thick layers of metal, and even then, missions like Galileo and Juno endure only because they dip into the worst regions for brief moments. To an astronaut, it would be one of the most hostile places imaginable, a silent storm of radiation swirling through an invisible ocean of magnetism. This magnetosphere doesn't simply trap particles, it shapes entire regions of space. As Jupiter spins, it drags its magnetic field with it, forcing charged particles into a rotating disk around the planet, the magnetodisk. Imagine an enormous flattened donut of plasma and magnetic field lines spreading outward in the planet's equatorial plane. This magnetodisk stretches far beyond the planet itself, containing regions of intense current that link the planet's upper atmosphere to its magnetic tail. These currents are like the veins of a giant organism, circulating energy across unimaginable distances. Within this system, the interactions between Jupiter's field, its moons, and the solar wind create a constant exchange of energy. Io, Europa, and Ganymede all orbit within this magnetic bubble, and each moon leaves its own electromagnetic signature, a footprint in Jupiter's field. The most dramatic of these is Io, whose volcanic emissions feed the magnetosphere with charged particles that flow along magnetic field lines back toward the planet's poles. There, the energy releases as breathtaking auroras glowing in ultraviolet light invisible to human eyes. Scientists have spent decades studying Jupiter's magnetic field, and yet it continues to surprise. The Juno mission revealed that the field changes subtly over time, a phenomenon called secular variation. This means that deep within the planet, the motions of metallic hydrogen are shifting, altering the field's shape and strength. It's a reminder that Jupiter is a living, dynamic world. Its magnetism isn't fixed. It's the expression of an ongoing process, as fluid and alive as the atmosphere swirling above. The scale of this magnetosphere also gives Jupiter a kind of cosmic influence. It carves out a bubble in the solar wind that dominates the space between the inner and outer planets. Even from 100 million kilometers away, Jupiter's magnetic presence can affect the behavior of charged particles, redirecting them, accelerating them, or capturing them entirely. To the Sun's constant wind of plasma, Jupiter is not just a planet. It's an obstacle, a massive magnetic mountain standing in the flow of interplanetary space. For all its might, the field has an elegance to it. Its invisible lines trace graceful arcs, converging at the poles, where they plunge into the upper atmosphere. There, they ignite the most brilliant auroras in the solar system, rings of glowing energy that outshine any northern lights on Earth. They pulse, twist, and shimmer, powered not by sunlight, but by the planet's own rotation and the dance of its moons. It's as though the king's enormous invisible cape has caught fire at its edges, flickering with light as it sweeps through the dark. To orbit Jupiter is to live within a storm of magnetism. Spacecraft passing near it feel the tug of its field, instruments registering its shifting pulses like a heartbeat. And yet, even in its violence, there is beauty. The magnetosphere, vast and unseen, is the planet's outermost layer, a shield, a sculptor, and a spectacle of physics at its most poetic. And at its farthest reaches, where the magnetic field stretches thin and interacts with the solar wind, the cape begins to shimmer. It flickers in colours no human eye can see, as electric currents stream along its lines toward the poles. There they collide with atoms in the upper atmosphere, releasing light and energy. Out of invisible motion, a visible wonder emerges. The auroras of Jupiter, brighter and stranger than any found beneath Earth's night sky. At Jupiter's poles, where magnetic field lines converge and dive into the atmosphere, the planet glows with a light show unlike anything on Earth. These are its auroras, vast circular ovals of ghostly light encircling each pole, glowing not in greens and reds like our northern lights, but in ultraviolet and infrared brilliance invisible to human eyes. If you could somehow watch them directly, they would appear as shimmering curtains of fire twisting and flickering in slow motion across a world the size of 1,000 Earths. Auroras form when charged particles crash into a planet's atmosphere, exciting atoms and molecules that then release light as they calm. On Earth, those particles come mostly from the Sun, carried by the solar wind. But Jupiter is different. Its auroras are powered primarily from within, by the planet's own immense rotation and magnetic machinery. Jupiter spins so quickly that its magnetic field whips around faster than the surrounding plasma can keep up, creating a generator effect that drives electric currents along magnetic field lines. When those currents reach the poles, they strike the upper atmosphere and release enormous amounts of energy as light. The result is a permanent ring of auroral emission around each pole, a glowing oval that never fully fades, even on the day side. This main oval marks the boundary between field lines connected to the planet's rapidly rotating magnetosphere and those stretching outward into the solar wind. It's effectively the visible edge of Jupiter's magnetic influence, drawn in light across the sky. Within this glowing perimeter are smaller moving features, arcs, flares, and footprints, each telling its own story about the planet's magnetic connection to its moons. Among these moons, Io plays the starring role. This small volcanic world constantly erupts sulfur and oxygen into space, feeding Jupiter's magnetosphere with charged particles. These ions are captured by the planet's magnetic field, forming a torus, a donut-shaped ring of plasma that orbits along with Io. The interaction between Io's motion and Jupiter's magnetic field generates powerful electric currents, which flow along magnetic field lines and converge near Jupiter's poles. Where those lines meet the atmosphere, they create bright spots within the auroral oval, the so-called Io footprints. These glowing footprints actually come in triplets: a main spot, a faint trailing arc, and a dim, more distant mark, a reflection of the way currents and plasma waves ripple through the field. It's as if Io is leaving glowing footprints across Jupiter's polar sky with every orbit, a reminder of the electromagnetic bond between moon and planet. Other moons also leave their mark, though less dramatically. Europa, Ganymede, and Callisto each produce their own auroral signatures, faint sparks along the Great Ring, revealing how interconnected this magnetic system truly is. What makes Jupiter's auroras even more extraordinary is their scale and intensity. The main ovals are enormous, thousands of kilometers across, and they radiate energy at levels far beyond any earthly aurora. If human eyes could see ultraviolet light, Jupiter's poles would blaze like cosmic fireflies, visible from millions of kilometers away. Spacecraft instruments detect bursts of radiation so powerful that they could power entire human civilizations for brief instants. Some of these bursts, called transient flares, occur when the planet's magnetic field reconnects, snapping and realigning in the turbulent interface between Jupiter's magnetosphere and the solar wind. When that happens, particles are accelerated to extreme speeds, colliding with the atmosphere and lighting up the polar regions with sudden flashes of brilliance. Unlike Earth's northern lights, which come and go with solar activity, Jupiter's auroras never really stop. They're a permanent feature, constantly fed by the planet's rotation and its internal engine. Even when the solar wind is calm, the auroras continue to burn, sustained by the electrical energy generated as Jupiter's magnetic field drags plasma around faster than gravity allows. In effect, the planet itself is the battery and its magnetic field the circuitry through which energy flows. To study these lights is to study the flow of plasma and current throughout the entire Jovian system. The patterns and brightness of the auroras tell scientists how the magnetosphere breathes, when it expands, when it contracts, and how energy circulates within it. By observing the flickering at the poles, researchers can map the invisible highways of charged particles that stretch for millions of kilometers around the planet. It's a cosmic feedback loop. The rotation of the planet drives the magnetic field. The field shapes the motion of plasma, and that plasma in turn powers the auroras that trace its path. Jupiter's auroras also reveal how different regions of space interact. Some emissions come from particles flowing inward along field lines that connect directly to the planet. Others come from the magnetotail far behind Jupiter, where the magnetic field reconnects with itself, sending surges of energy back toward the poles. These bursts create sudden brightenings and spirals within the auroral ovals, brief but spectacular signatures of the magnetosphere's restless energy. To observers, they might look like glowing storms of light, curling and unwinding in rhythmic pulses. Viewed through the right instruments, the auroras are almost alive. Ultraviolet cameras capture their outlines as glowing rings. Infrared sensors reveal hotspots where the atmosphere warms under bombardment. Some of the energy released heats the upper layers of Jupiter's atmosphere to unexpectedly high temperatures, creating a mysterious phenomenon scientists still puzzle over. It's as though the auroras act not just as decoration, but as a heating system, redistributing energy and driving circulation across the poles. The visual effect would be breathtaking. From orbit, the poles appear haloed in light, broad ovals shimmering with slow waves and flares. Filaments of brightness twist outward into space, where magnetic field lines carry their energy toward the magnetotail. Every few minutes, bright spots flicker on and off, the telltale footprints of Io or Europa tracing their invisible paths. Even when viewed through the faint glow of reflected sunlight, the auroras dominate the poles, pulsing with an energy both serene and immense. It's humbling to realize that all this grandeur comes from invisible forces, electrons and ions guided by magnetic fields, colliding with atoms high above the clouds. Yet from that unseen motion emerges something that feels almost spiritual. Light, born from magnetism. Order emerging from chaos. In Jupiter's polar skies, physics becomes poetry. The Great Red Spot may be the planet's most famous feature, but the auroras are its soul, an ever-burning crown of light, fed by motion, magnetism, and time. They are the glowing edges of an unseen empire stretching into space, linking Jupiter to its moons and to the solar wind beyond. And far beneath those glowing rings and spirals, the rest of the planet continues its quiet rotation. Storms churn, lightning flashes, and belts of cloud ripple endlessly around the globe. Even the King's invisible cape has edges, and at those edges light takes form. Yet Jupiter's beauty doesn't end at its poles. Beyond the auroras, farther from the planet, lies another gentler wonder, a crown of dust and debris encircling the giant like a faint halo in the dark. Even a king, after all, wears rings, quiet, delicate ones. Jupiter wears a crown, but it's so faint and delicate that for centuries no one knew it existed. Unlike Saturn's glorious shimmering rings that blaze even through a small telescope, Jupiter's are almost invisible, made not of gleaming ice, but of dust so fine it scatters only the faintest light. If Saturn's rings are a showpiece, Jupiter's are a secret, a subtle, understated halo that whispers rather than shines. These fragile rings were first discovered in 1979, when the Voyager 1 spacecraft passed behind Jupiter and caught sunlight glinting off a thin band of particles encircling the planet. What the spacecraft saw was astonishingly faint, a narrow, dusky ribbon just above the cloud tops, stretching around the equator like smoke caught in orbit. Since then, later missions such as Galileo and Juno, along with powerful Earth-based telescopes, have revealed the system in greater detail. What they found was not one ring, but several, each with its own tone and texture. The main ring, the inner halo, and the outer gossamer rings. The main ring is the brightest, though that's a generous word here. If you were hovering nearby, you might only notice it when sunlight strikes it from behind, scattering forward through the fine dust. It lies just above the cloud tops, extending about 55,000 kilometers from the planet's center. Yet its thickness is only a few dozen kilometers. Within this slender space floats a haze of tiny grains, mostly microscopic fragments of silicate rock. These particles are continually ground, launched and replenished by the activity of small inner moons. Two of those moons, Metis and Adrastea, orbit within the main ring itself. They act as both sources and sculptors of the dust. When micrometeoroids, tiny, fast-moving bits of space debris, collide with their surfaces, the impacts kick up clouds of fine particles that drift outward, forming the ring. Each collision is like a puff of cosmic smoke, and over time those puffs create a continuous veil. The ring's faint structure reflects a balance between creation and erosion. Dust constantly lost to Jupiter's gravity, radiation pressure, and magnetic forces, and constantly replaced by new material from the moon's surfaces. Closer to the planet lies the halo, a thicker, more diffuse torus of dust that glows faintly in forward-scattered light. The halo isn't a neat, flat band like the main ring, but a puffy, cloud-like structure extending both above and below the ring plane. Here, Jupiter's strong magnetic field plays a major role, tugging on charged dust grains and causing them to move in looping, tilted paths. Instead of orbiting neatly, they spiral slightly, giving the halo its soft, diffuse shape. This inner region catches the planet's faint reflected light and bends it like mist around a lamp, a glowing aura that only reveals itself under the right conditions. Farther out, the main ring gives way to the gossamer rings, the most ethereal of all. These are formed by two slightly larger moons, Amalthea and Thebe, which orbit farther from Jupiter. Their faint debris trails stretch inward toward the planet, creating overlapping sheets of dust so thin that they are nearly transparent. These gossamer rings are so delicate that if you held a handful of the material together, it would be barely visible even under sunlight. Their name fits perfectly. Gossamer, meaning something so fine it almost isn't there. Jupiter's rings are visible primarily when sunlight shines through them from behind, a technique known as forward scattering. In this orientation, light bounces through the dust and becomes visible to spacecraft cameras. From most other angles they vanish, blending perfectly into the blackness of space. It's this elusive nature that kept them hidden for so long. To the human eye, Jupiter appears as a planet with no adornments. Only when the lighting is right does its subtle crown appear, faintly gleaming like dust motes floating in a sunbeam. The dynamics of these rings are surprisingly complex. Tiny dust grains feel not only Jupiter's gravity, but also the drag of the planet's magnetic field, solar radiation, and the gravitational pull of nearby moons. Each of these forces nudges the particles, gradually altering their orbits. Some drift inward until they are vaporized in the upper atmosphere. Others are pushed outward, spreading the ring's edges. In this way, Jupiter's rings are constantly in motion, eroding, replenishing, and reshaping themselves on timescales of months or years. Micrometeoroid impacts are the quiet sculptors of this process. The inner moons endure a steady bombardment of tiny projectiles travelling tens of kilometers per second. Each strike releases dust that joins the ring, while the ring itself in turn is slowly eroded by the same impacts. The balance between destruction and renewal keeps the system stable, fragile yet persistent. It's an understated act of maintenance, like a crown that polishes itself through constant use. Unlike Saturn's rings, which gleam with ice and reflect sunlight like mirrors, Jupiter's dusty rings absorb much of the light that hits them. Their colour, when seen up close, is a muted red-brown, matching the silicate composition of their source moons. The lack of icy material is another reason they appear so dim. Near the sun, volatile ices can't survive. They sublimate away, leaving only rock and dust behind. Jupiter's warmth ensures that its rings remain made of stone, not frost. Still, their faintness carries a kind of charm. In a solar system of spectacular rings and moons, Jupiter's are the quiet ones, modest, transient, but elegantly formed. They remind us that not all grandeur shouts, some simply glows softly in the dark. It's as if the king of planets decided he didn't need a golden crown at all, just a thin band of dust, an accessory that whispers, "I could shine brighter, but I don't need to." The ring system also plays an important scientific role. By studying how light scatters through the dust, scientists can learn about the size, composition, and even the charging of individual particles. These observations reveal how dust behaves in environments dominated by magnetic fields, insights that apply not just to Jupiter, but to other planets, moons, and even the dusty disks around distant stars. Every grain tells a story of collisions and electric forces, of the balance between gravity and motion. From certain angles, especially when illuminated by the sun from behind, Jupiter's rings take on a ghostly beauty. They appear as pale arcs of light curving around the planet, faint but graceful, like the outline of a forgotten halo. From these views, captured by spacecraft and telescopes, you can almost sense the delicacy of their construction. Billions of tiny particles moving together in a quiet ballet. It's the most fragile jewellery in the solar system, endlessly remade by dust, light, and time. Though faint, these rings remind us that even a giant world wears the marks of its surroundings. They are the residue of collisions, the echoes of small moons pelted by cosmic debris. Every mote of dust is a memory of impact and transformation, still circling long after the event that created it. Jupiter's rings are the softest statement of planetary majesty imaginable. A crown made not of light, but of shadow, almost unseen, but perfectly in character for a world that prefers grandeur in motion rather than appearance. A king's crown, yes, but an understated one, worn lightly in the cosmic dark. And beyond that delicate crown lies an entire court of companions, dozens of moons, large and small, each with its own story and its own place in the grand orbit of the King of Planets. Encircling Jupiter is a kingdom of worlds, a miniature solar system in its own right. Dozens of moons orbit the giant, each one distinct, each with a story carved from gravity and time. Together, they form a celestial court that mirrors their planet's grandeur, some small and ragged, others immense and stately, and a few so extraordinary that they could be planets themselves if they orbited the sun instead. Astronomers have identified nearly 100 of these moons so far, and more continue to be discovered as telescopes improve. They fall roughly into two great families. Closest to Jupiter are the regular satellites, the Galilean moons, and a handful of smaller companions that orbit in near-perfect circles aligned neatly with the planet's equator. Farther out are the irregular moons, captured wanderers that loop around Jupiter in stretched, tilted, and sometimes backward orbits, their paths tracing the aftershocks of ancient encounters. The Galilean moons, Io, Europa, Ganymede, and Callisto, are the crown jewels of Jupiter's court. They were discovered in 1610 by Galileo Galilei, who turned his small telescope toward Jupiter and saw, to his astonishment, 4 tiny stars lined up beside it. Night after night he watched them change position, moving in step around the planet. It was the first clear proof that not everything in the heavens revolved around Earth, and in that simple observation the universe grew larger. These 4 worlds are among the most fascinating objects in the solar system, each a self-contained world, shaped by the gravity of the giant they orbit. Beyond them lies a much more chaotic realm. The irregular moons are a mixed collection, captured asteroids, cometary remnants, and shattered fragments of earlier moons torn apart by collisions. They orbit much farther out, often in clusters that share similar paths. Some move prograde, in the same direction as Jupiter's rotation, while others move retrograde, circling the opposite way like rebellious courtiers. Their orbits are steeply inclined, some tilted almost sideways to the planet's equator, suggesting they were not born here, but taken in later, strays from the early solar system drawn in by Jupiter's enormous gravity. The capture of these moons wasn't gentle. In the chaotic early days of the solar system, Jupiter's gravity acted like a cosmic net. snagging passing bodies that wandered too close. Some were slowed by collisions with gas or dust in the planet's extended atmosphere, losing just enough energy to remain trapped. Others arrived as parts of binary systems, pairs of small bodies orbiting each other, and when Jupiter's gravity tore the pair apart, one escaped while the other was captured. Many of these irregular moons now form families of their own, likely the debris of larger bodies shattered by impacts long ago. Astronomers can trace their shared origins by comparing their orbits and colours, revealing clusters that tell tales of ancient destruction. Closer in, the story's more orderly but no less dramatic. The regular moons follow paths carved by resonance, delicate gravitational rhythms that tie their orbits together. Io, Europa and Ganymede are locked in a perfect dance. For every orbit Ganymede completes, Europa goes around twice and Io 4 times. This gravitational synchrony keeps their orbits slightly stretched, generating internal tides that flex and heat their interiors. It's a quiet but relentless process, gravity kneading worlds like dough, creating energy from motion. This tidal heating explains much about the character of Jupiter's major moons. Io, the innermost, is a world of fire, its surface erupting with hundreds of active volcanoes. Next comes Europa, where that same tidal energy melts ice from below, creating a hidden ocean beneath its frozen crust. Ganymede, the largest moon in the solar system, generates its own magnetic field, suggesting a metallic or salty ocean inside. And then there is Callisto, cratered and ancient, where tidal forces are weaker and the surface has remained largely unchanged for billions of years. Together, these 4 worlds form a gradient, from fire to water to silence, each one sculpted by its distance from the giant. The smaller inner moons play quieter roles. Metis, Adrastea, Amalthea, and Thebe orbit close to Jupiter's cloud tops, contributing dust to the planet's faint ring system. They're irregularly shaped and heavily battered, remnants of the early system that somehow avoided destruction. Despite their size, they are vital contributors to the ongoing life of Jupiter's rings, tiny attendants keeping the crown intact. Then there are the outer irregular moons, far beyond the Galileans, moving in slow, looping orbits that can take hundreds of days to complete. Many of them are only a few kilometers wide, captured fragments, each with its own unique tilt and orientation. Some of these moons orbit so far out that the Sun's gravity begins to compete with Jupiter's for their loyalty. It's a delicate balance, a reminder of how complex and interconnected this system truly is. Jupiter's gravitational influence extends so far that its family of moons and captured debris could almost be considered a miniature version of the solar system itself. The planet's gravity dominates a vast region called its hill sphere, an invisible boundary where Jupiter's pull overpowers the Sun's. Within this space, it has gathered companions of every kind: volcanic, icy, rocky, and dusty. Each one moves to a rhythm set by the planet's mass and motion. What makes these moons so fascinating isn't just their variety, but their interactions. Tidal forces stretch and squeeze them, magnetic fields connect them, and gravity keeps them locked in a choreography that has lasted for billions of years. Io's volcanic plumes feed Jupiter's magnetosphere with sulfur and oxygen, while Europa's icy surface hints at hidden oceans that could harbour the ingredients for life. Ganymede's size and magnetic field make it more like a planet than a moon, and Callisto remains a frozen relic of the solar system's past. Even the tiniest moons play their part, shaping rings, disturbing dust, and occasionally colliding, creating new fragments to join the dance. It's easy to forget that each of these moons, even the smallest, is a world with its own gravity, landscapes, and mysteries. Standing on Io, you would see Jupiter looming impossibly large in the sky, filling half the heavens, its clouds shifting and flashing with distant lightning. From Europa, you might watch that same planet rising and setting through cracks in the ice. From Ganymede or Callisto, you would see the planet as a striped marble in the darkness, its light reflecting off the icy plains. Each moon experiences Jupiter differently, but all are bound by the same gravitational bond. For astronomers, studying this system is like reading a history book written in orbits and tides. The moons record the solar system's story of formation, collision, and capture. They show how gravity sculpts worlds, not just in shape, but in destiny. And as missions like Juno and future explorers like Europa Clipper continue to study these moons up close, new chapters are still being written. Jupiter's court is one of endless motion, a grand, slow waltz of dozens of bodies held together by invisible threads. It's a family shaped by chaos and order alike, where every moon has its place and its purpose. Some whisper of fire, others of ice, and some of silent time. And among them all, one stands out as the most restless, a volcanic herald whose surface is constantly remade by eruptions and tides. The first to speak in this planetary symphony of worlds is Io, the stormy moon of fire and ash. Io is a world that never sleeps. It's the most volcanic body in the solar system, a restless moon whose surface is constantly erupting, reshaping and renewing itself. At any given moment, somewhere on Io, a volcano is blowing molten sulfur into space, painting the landscape in shades of yellow, orange, and red. To look upon it is to see a world forever caught in motion, a planet-sized cauldron powered not by sunlight or radioactivity, but by the invisible tug of gravity. The source of Io's energy lies in its orbit around Jupiter, where gravity becomes a kind of slow drumbeat of destruction and renewal. Io's path is not perfectly circular. Because of a gravitational resonance with Europa and Ganymede, it moves in a slightly stretched ellipse, drawing closer to and farther from Jupiter during each orbit. Every time it approaches, Jupiter's immense gravity pulls harder, flexing the moon's interior. Then, as Io moves away, that pull relaxes. The entire moon stretches and compresses with each cycle, creating enormous friction inside its mantle. This tidal flexing releases as much heat as 1 million terrestrial volcanoes melting rock and driving the constant eruptions that define its surface. Imagine the entire crust of a world rising and falling by dozens of meters over and over again for billions of years. That's Io. Its surface, which should have cooled and hardened long ago, instead behaves like a thin crust over a simmering ocean of magma. Where the pressure becomes too much, it cracks, and fountains of molten sulfur and silicate rock burst forth, some shooting hundreds of kilometers high. These eruptions can last for months, even years, covering vast regions with new layers of lava and frozen sulfur frost. When spacecraft like Voyager, Galileo, and Juno have glimpsed Io, they've seen a surface that seems alive, glowing with active plumes, glowing lava lakes, and constantly shifting colours. Unlike Earth's volcanoes, which cluster around tectonic boundaries, Io's volcanoes are scattered everywhere. The entire moon is geologically active from pole to pole. Its mountains rise higher than Mount Everest, not from plate collisions, but from the buckling of the crust under internal pressure. Vast plains of frozen sulfur stretch between the peaks, mottled by bright yellows and deep reds from chemical reactions on the surface. The colours come from sulfur in different forms: bright yellows from freshly erupted deposits, oranges and browns from older, more weathered material, and darker reds where heat has baked the minerals into new compounds. Seen from orbit, Io looks like an artist's palette left too long in the sun. Brilliant, but chaotic. The plumes that rise from its volcanoes are immense, dwarfing anything seen on Earth. Some soar over 300 kilometers into space, so large that they can be seen silhouetted against the blackness behind the moon. They're made of sulfur dioxide gas and fine dust, hurled upward by explosive eruptions, then falling back like a thin toxic snow. These plumes help form a faint, patchy atmosphere that clings to the moon for only short periods before freezing or escaping into space. Each eruption briefly replenishes it, keeping Io surrounded by a thin, ever-changing haze. But Io's influence doesn't end with its own sky. The gases escaping from its volcanoes are caught by Jupiter's magnetic field, stripped into ions of sulfur and oxygen, and swept into orbit around the planet. There they form a vast glowing ring of charged particles known as the Io plasma torus. This invisible river of ionized gas encircles Jupiter, connecting the moon directly to the planet's magnetic system. As Io moves through it, electric currents flow along magnetic field lines between the two worlds, a gigantic natural circuit stretching nearly 500,000 kilometers. The energy carried by these currents helps to power Jupiter's auroras, linking the moon's volcanic fury to the shimmering lights at the planet's poles. For Io, this relationship is both beautiful and brutal. The magnetic field bombards the moon with radiation, constantly ionizing its atmosphere and surface. It's one of the harshest environments anywhere in the solar system. Yet through this constant exchange, Io and Jupiter remain intertwined, a fiery moon feeding an invisible sea of magnetism. It's a reminder that in space, everything is connected, even across distances that would swallow whole worlds. The landscape of Io is a contradiction in motion. There are no impact craters visible because the surface is constantly renewed, old scars erased by new lava flows. Every few million years, the entire crust may be recycled, resurfaced entirely by volcanic activity. It is in essence a living world, but one that thrives on destruction. The surface is dotted with hundreds of active centers, some with enormous lava lakes, others with towering vents. The most famous of these, Loki Patera, is a vast caldera over 200 kilometers across, a volcanic depression larger than some countries on Earth. Observations show it brightening and dimming over time as the surface crust periodically sinks, breaks apart and reforms over a molten lake below. If you could somehow stand on Io, safely shielded from the radiation, and somehow ignore the minus 160 degrees Celsius temperature, the view would be unforgettable. The sky would be a pale yellow from the sulfur haze, and Jupiter would dominate the heavens, its immense face 50 times wider than Earth's moon as seen from home. Across the horizon, pillars of volcanic gas would rise silently, glinting faintly in the dim sunlight. You'd feel no sound, no wind, only the slow, continuous shifting beneath your feet as the moon flexed under Jupiter's gravitational pull. Beauty can be loud even in silence, and here the noise is written in colour and motion rather than sound. Io's unending activity makes it a window into processes that shaped the early solar system. Tidal heating, that steady flexing and friction, may have played a role in keeping young worlds warm billions of years ago. Even now it shows scientists how energy can flow from gravity alone, without the need for sunlight or radioactivity. It also offers a contrast to its quieter siblings. While Io burns, others freeze. Its violent surface stands in sharp contrast to the calm ice of Europa and Ganymede, where that same tidal energy is spent melting oceans beneath frozen shells instead of fueling volcanoes. Every eruption, every plume, every glowing lake of molten rock is part of a cycle as old as the solar system itself, a balance between motion, heat, and gravity. Io teaches that planets and moons are not static places. They live, change and evolve. Its fire is a reminder of the energy still hidden within the bones of worlds, waiting only for the right kind of motion to wake it. From the distance of space, Io's golden glow and its trails of sulfur dust make it look almost gentle, a candle flickering in the shadow of Jupiter. But up close, it is chaos given form, a world forever breaking and remaking itself under the pull of its giant parent. And just beyond it, orbiting in the same great rhythm, lies another moon born from that same gravitational tension, a frozen world hiding an ocean beneath its shell. From fire we move now to ice, and to a place where warmth is hidden under silence. Europa is one of the most beautiful enigmas in the solar system, a world wrapped in ice, silent on the outside but whispering secrets from below. Its surface gleams pale and smooth, a frozen mirror reflecting the faint sunlight that reaches Jupiter's domain. But beneath that frozen shell, scientists believe there may be an entire ocean, vast, dark, and warm enough to move. If true, Europa could hold more water than all of Earth's oceans combined. It's the quietest world in Jupiter's court, and yet beneath the silence something stirs. At first glance, Europa looks calm, almost pristine. There are few impact craters, which means the surface must be young, constantly renewed. Instead of mountains or canyons, the moon is etched with long, dark streaks that crisscross its icy crust. The famous lineae that stretch for thousands of kilometers. These marks look like cracks in old paint, but they are scars of motion. As Europa's interior flexes under Jupiter's gravitational pull, the ice shell stretches and fractures. When the cracks open, material from below rises to fill them, leaving behind dark, reddish-brown ribbons that trace the paths of stress across the moon's surface. Those streaks, and the broken regions known as chaos terrains, are our first clues that Europa's shell is not solid all the way down. The surface seems to float atop something that can flow, likely a global ocean lying beneath 10 to 30 kilometers of ice. In some regions, the ice looks shattered and rearranged, as if huge slabs have drifted and refrozen, like pack ice on Earth's polar seas. The patterns suggest motion beneath the crust, and motion means warmth. That warmth comes from the same tidal dance that powers Io's volcanoes, though Europa's response is gentler. Locked in orbital resonance with Io and Ganymede, Europa is constantly stretched and squeezed by Jupiter's gravity. This rhythmic flexing generates heat inside the moon, not enough to melt the surface, but enough to keep a subsurface ocean from freezing solid. The process is subtle but relentless, energy drawn from the moon's orbit and converted into internal warmth, a gravitational heartbeat that has pulsed for billions of years. Evidence for this hidden ocean comes from several lines of observation. When the Galileo spacecraft flew past Europa in the 1990s, it detected slight fluctuations in the moon's magnetic field. These variations hinted at a layer of electrically conductive material beneath the surface, most likely a salty ocean. Later observations from the Hubble Space Telescope revealed faint plumes of water vapor rising from the moon's southern regions, shooting hundreds of kilometers into space before falling back to the surface. These plumes, if confirmed, would be tantalizing evidence of water escaping from below, geysers on an alien sea. Europa's surface itself tells a story written in ice and salt. Spectroscopic studies suggest that the dark material along its fractures and chaos regions contains salts similar to those found in Earth's oceans: magnesium sulfate, sodium chloride, perhaps even other minerals that hint at chemical interactions between rock and water. It's possible that Europa's ocean lies atop a rocky seafloor, where water and rock meet in darkness. If so, chemical reactions could occur there, much like those around hydrothermal vents on Earth's ocean floors. Those vents, on our planet, teem with life. But talk of life on Europa must be made carefully. The ingredients are enticing: water, chemistry, and energy. But that doesn't guarantee biology. The ocean may be warm and salty, yet lifeless, a quiet abyss of chemistry without consciousness. Still, the possibility remains, and that's enough to hold the world's imagination. Even the simplest microbial existence, clinging to rocks beneath kilometers of ice, would change how we see life in the cosmos. It would mean that life is not a rare accident, but a natural outcome of planetary evolution, something that arises wherever water and energy find balance. The mystery is deepened by how little we can see. Europa keeps its ocean hidden, speaking only through subtle clues: magnetic ripples, surface fractures, spectral fingerprints, and the occasional whisper of vapour above the poles. It's been called the sheerest ocean in the solar system, always covered, never seen directly but endlessly fascinating. Unlike Io, which shouts its presence with volcanic fury, Europa keeps its secrets buried beneath an icy calm. Scientists believe that the topmost layer of the ocean may be in direct contact with the ice above, creating zones where freezing and melting constantly trade places. Salt-rich water could rise through cracks, freeze at the surface and deposit its minerals in dark streaks, only to sink again when the ice melts. In this way, Europa's crust might act like a slow, planetary lung, breathing water up and down through fractures, circulating nutrients and heat. The surface patterns, from smooth plains to jumbled chaos, could be the frozen fingerprints of that hidden respiration. The idea of a world with a buried ocean has captivated scientists and dreamers alike. Missions are now being designed to explore it more closely. NASA's Europa Clipper spacecraft, set to launch soon, will make dozens of flybys to map the ice, measure its chemistry, and search for plume activity. Another mission, the European Space Agency's JUICE spacecraft, will also study Europa alongside Ganymede and Callisto, looking for evidence of internal oceans and magnetic signatures. With every orbit, we draw a little closer to understanding what moves beneath that icy crust. The challenges of exploring Europa are immense. Temperatures hover around -160 degrees Celsius, and Jupiter's radiation belts flood the region with charged particles that would disable an unprotected probe in minutes. Any future lander will need thick shielding and delicate instruments designed to survive the hostile environment. But even with these challenges, the allure is irresistible. The chance to sample water that may have been sealed off for billions of years is too tempting to ignore. Europa invites quiet wonder. It doesn't dazzle with colour or noise. It doesn't roar like Io or shine like Jupiter's storms. Its beauty lies in suggestion, the smooth glint of sunlight on its ice, the delicate tracery of its cracks, and the promise of an ocean moving unseen below. It is a reminder that not all life, or even all hope, needs to announce itself loudly. Sometimes, the most profound possibilities lie hidden beneath layers of silence. If Europa truly harbours an ocean, it would be one of the most remarkable environments in the solar system, dark, deep, and untouched since its formation. Whether it's lifeless or lively, it represents an entire world's worth of mystery, a place where gravity, water, and chemistry have conspired to keep a secret for billions of years. And that secret might not stay hidden forever. Future missions may one day pierce the ice or capture droplets from a passing plume, revealing the chemistry of that buried sea. Whatever they find, salts, organics, or something entirely unexpected, will deepen our understanding of how worlds evolve in the cold outer reaches of space. For now, Europa remains quiet, a world of ice and shadow holding its breath beneath Jupiter's watchful eye. And just beyond it waits another moon, larger, magnetized, and carrying its own story of oceans and frozen time. A clue in Jupiter's magnetic field leads outward, toward the next great world in this moonlit court. Ganymede is the monarch among moons, the largest of them all, even bigger than the planet Mercury. Yet despite its size, it carries itself with quiet dignity, a calm world orbiting a turbulent giant. It is a place of paradoxes, vast and ancient, scarred yet serene, and deep within its frozen heart, it holds a secret no other moon can claim, a magnetic field of its own. Discovered by Galileo in 1610, along with its siblings Io, Europa and Callisto, Ganymede immediately stood apart. It was not just large, but luminous, reflecting sunlight off an icy crust, crisscrossed with pale grooves and dark patches. When spacecraft later revealed its true nature, scientists realized it was not merely a frozen rock, but a differentiated world, a planet in miniature, complete with a core, mantle and crust layered like Earth itself. Beneath its surface lies a deep ocean, trapped between sheets of ice, and at its very centre, molten iron still flows, turning slowly and generating a magnetic field that hums faintly through space. That magnetic field is Ganymede's defining feature. Among moons, it is unique. Even Earth's moon and Mercury's weak magnetism pale beside it. The field creates tiny auroras at Ganymede's poles, shimmering in ultraviolet light where charged particles collide with the thin traces of its atmosphere. More intriguingly, this field interacts directly with Jupiter's enormous magnetosphere, forming a miniature magnetic bubble within the larger one, a magnetic world orbiting within a magnetic kingdom. The effect is a dynamic dance of currents and fields, a constant interplay between the moon and its planet. The existence of this field tells us something profound about Ganymede's interior. To sustain it, the moon must have a molten metallic core, most likely iron or iron sulfide, still in motion after billions of years. That motion drives an internal dynamo, much like Earth's, powered by slow cooling and the crystallization of heavier elements toward the centre. It is as if, deep within this frozen world, there lies a hidden furnace, an iron heart that still beats faintly beneath the ice. Above that core lies a thick mantle of silicate rock, and above that layers of ice and possibly water. Models suggest that Ganymede's ocean, if it exists, might be sandwiched between layers of ice, forming a layered ocean structure. Ice, then liquid water, then more ice. In total, this ocean could contain more water than all of Earth's combined, though it remains sealed beneath hundreds of kilometers of frozen crust. Even so, signs of motion persist. Magnetic measurements indicate that the ocean is salty and conductive, its movement subtly influencing the moon's field. In this way, Ganymede's magnetism not only hints at metal below, but water above. A dual nature of fire and ice intertwined. The surface of Ganymede tells the story of a world that once stirred with tectonic energy. Its most striking features are its grooved terrains, long parallel ridges stretching for hundreds of kilometers across the icy plains. These grooves are believed to be the result of tectonic stress, formed when the crust was pulled apart and icy material from below welled up to fill the gaps. They crisscross the surface in intricate patterns, overlapping older impact scars and dark regions. Some are smooth and bright, others fractured and shadowed, giving the moon a textured look unlike any other body in the solar system. Between these grooved expanses lie ancient dark terrains, remnants of Ganymede's original crust. They are heavily cratered, scarred by impacts dating back billions of years, their features softened over time by slow flows of ice. These darker regions contrast sharply with the bright streaked plains, telling a geological story of renewal and preservation, of a moon that once flexed and shifted before cooling into relative stillness. It's a record of activity frozen in place, a silent archive of a more restless past. Despite its violent history, Ganymede today is a world of comparative calm. It lacks Io's fury and Europa's fragility, standing instead as a monument to stability. Its gravity is strong enough to shape a substantial atmosphere, thin and tenuous, made mostly of oxygen molecules broken from the surface ice by sunlight. This atmosphere is far too thin to breathe, but it adds to the sense that Ganymede is a complete, self-contained world. It is not merely a satellite, it is a planet that happens to orbit another. Viewed from above, Ganymede's landscape is hauntingly beautiful. Bright rays of ice extend from craters, gleaming against the darker plains. Long ridges stretch to the horizon, their edges softened by time. In the dim light of Jupiter's reflected glow, the surface glitters faintly, a frozen cathedral beneath the eternal night. The grooves form vast geometric patterns, as though some ancient architect had drawn them by hand. Yet all of this grandeur hides an interior alive with unseen motion. Deep below the ice, the molten core continues to turn, its magnetic whisper threading through the layers above. Ganymede is, in every sense, a cathedral moon with iron bells within. The interactions between Ganymede and Jupiter create a constantly changing electromagnetic landscape. As the moon moves through Jupiter's magnetic field, charged particles stream past it, sometimes generating faint auroras in Jupiter's atmosphere where field lines connect. These subtle traces provide scientists with a natural laboratory for studying magnetism on both planetary and moon scales. When spacecraft fly by, their instruments detect not only magnetic variations but also hints of the moon's internal structure, allowing us to peer indirectly through layers of rock and ice. If one could stand on Ganymede, the sky would be magnificent. Jupiter would hang enormous above the horizon, its clouds faintly coloured by distance, surrounded by the other moons moving along their paths. The surface beneath your feet would crunch softly with frost, the silence so profound that you could almost hear the faint hum of magnetism, the slow turning of that iron heart deep below. Ganymede's serenity belies its complexity. It bridges worlds, between rock and ice, between motion and stillness, between the inner warmth of metal and the outer chill of space. It's a moon that has found equilibrium, carrying both the memory of its fiery beginnings and the patience of its frozen present. In its quiet endurance, it embodies a kind of cosmic grace, a reminder that strength doesn't always roar. Sometimes it resonates softly, like the deep tone of an unseen bell. For scientists, Ganymede offers a glimpse of what large icy worlds can become: stable, self-sustaining, and layered with history. Its magnetic field gives clues to how planetary dynamos evolve, while its potential ocean hints at the conditions that might foster chemistry, if not life. Future missions will study it closely, mapping its magnetism, measuring its crust, and searching for signs of activity beneath the surface. Each pass brings us closer to understanding how such a complex moon came to be. And as we drift outward from Ganymede's orbit, the light begins to fade. The next moon lies farther from the sun and farther from Jupiter's warmth, dimmer, darker, colder, yet still quietly stirring in its own ancient way. Callisto is the elder of Jupiter's great moons, ancient, quiet, and unhurried. While its siblings dance to the rhythms of tides and magnetism, Callisto drifts serenely on the outskirts of the system, far enough from Jupiter to escape the tug-of-war that stirs the others. Its surface, dark and cratered, has remained largely unchanged for billions of years. It is a world that remembers everything. Every impact, every scar, every ancient story is still written upon its face. If the moons of Jupiter were a royal court, Callisto would be the archivist, patient, reserved, and utterly unwilling to throw anything away. Seen through a telescope, Callisto appears mottled and subdued, its shades of grey and brown blending into a calm, dusky sphere. But up close, spacecraft have revealed a surface unlike any other, a dense quilt of craters upon craters, packed so tightly that even the craters themselves have craters. There is no sign of volcanic activity, no ridges or grooves like those etched into Ganymede, no flowing ice plains like Europa's. It is as if the moon froze early in its history and has slept ever since, quietly collecting the signatures of cosmic time. This lack of geological activity makes Callisto a kind of planetary fossil. Its surface preserves a record of impacts stretching back to the earliest days of the solar system, when asteroids and comets still roamed freely, colliding and merging to form planets and moons. Each crater tells part of that story, from vast multi-ringed basins to the smallest pockmarks left by ancient debris. The largest, Valhalla, spans nearly 4,000 kilometers, an enormous concentric pattern of ridges that ripples outward from a central impact point. It's not just a crater, it's a frozen echo of violence that shook the entire moon and left a scar visible across half its surface. Unlike its more dynamic siblings, Callisto shows little evidence of internal differentiation. When the moon formed, it seems to have never fully melted inside, meaning that rock and ice remain mixed throughout rather than separating into layers of core, mantle, and crust. This gives it a lower density and a simpler structure, a world built more from ancient ingredients than from internal alchemy. In many ways, it's the most primitive of the Galilean moons, a snapshot of what the early building blocks of planets might have looked like before heat and gravity reshaped them. Yet even this quiet world may hide a few surprises beneath its stillness. Magnetic readings taken by the Galileo spacecraft hinted that Callisto might possess a subsurface ocean, much like Europa and Ganymede. The evidence isn't as strong, but it's intriguing. Subtle changes in the magnetic field suggest a conductive layer beneath the surface, possibly a salty liquid water ocean trapped under hundreds of kilometers of ice. If it exists, it would be a dark, cold sea, far from the warmth of the sun or the tidal heating of Jupiter, sustained only by the slow decay of radioactive elements within. This idea adds depth to Callisto's serenity. Beneath its battered crust, there may be movement after all, slow convection, faint warmth, maybe even the chemistry of water and rock mingling in silence. But on the surface, nothing betrays it. The moon presents itself as timeless and still, a monument to endurance rather than activity. It has no magnetic field, no geological renewal, no atmosphere of note beyond a thin wisp of carbon dioxide and oxygen. It simply circles Jupiter, observing, unchanged. Callisto's quiet is its greatest gift. In that stillness lies history, the oldest, most complete record of the early solar system anywhere beyond the asteroid belt. Scientists often describe it as a time capsule, a body that preserves conditions from the epoch of planetary formation. By studying its craters, composition, and surface chemistry, we gain glimpses of what the solar system looked like 4 billion years ago, when impacts were frequent and young worlds were just beginning to take shape. The contrast with its siblings is striking. Io burns, Europa hides an ocean beneath restless ice, and Ganymede hums with magnetism. Callisto does none of these things. It remains at peace, orbiting far enough from Jupiter that tidal forces are weak. Its interior spared the flexing and friction that have kept the others geologically alive. That distance has made it stable, a moon untouched by the storms of its family. Where the others evolve, Callisto endures. Its landscape is full of quiet poetry. Sunlight glints softly on its crater rims, Long shadows stretch across ancient basins, and the dark plains in between are dusted with fine ice grains. It is a world of gentle contrasts, light and dark, old and older still. Some regions are so ancient that they may have existed since the solar system's first few 100 million years, never resurfaced, never erased. If you could stand there and look around, you'd be gazing at the oldest ground your feet could ever touch. Terrain that predates nearly everything else you know. In that sense, Callisto is not lifeless so much as timeless. It is a world content to remember. Every scar is a story, every crater a chapter written in stone and ice. Its refusal to change is what makes it so valuable. In an environment where so many worlds are restless, Callisto's stillness is its strength, a stable archive, holding on to the memory of the solar system's violent youth. And yet, even this moon of memory may not be entirely static. The faint possibility of a hidden ocean means that beneath its ancient shell, a slow whisper of motion might still exist. Perhaps tiny currents stir in that buried water, or minerals drift from rock into brine, continuing a conversation that began billions of years ago. If so, Callisto's calm is not absolute. It may simply be the patience of a world that moves on timescales too vast for human imagination. There's a quiet humour to Callisto's role among Jupiter's moons. While Io continually repaints itself and Europa refreshes its ice, Callisto just shrugs and keeps everything. It's the cosmic equivalent of an old librarian who refuses to discard a single volume, every crater catalogued, every fragment filed away. If some future explorer wished to understand the earliest chapters of Jupiter's realm, this would be the place to visit. The answers aren't hidden in change here, but in endurance. From a distance, Callisto may seem unremarkable compared to its more dramatic companions, but that's part of its charm. In a system dominated by motion and energy, it is the moon of reflection, the elder statesman of Jupiter's court, carrying the memories of a time before harmony, before orbit stabilized and chaos calmed. It is a survivor, quietly orbiting the giant it has known since the dawn of time. And as we drift back from Callisto, from this archivist who guards the memories of creation, we return to the source of all their stories, the giant that binds them together, whose gravity set their orbits, and whose pull keeps the rhythm of their tides. It's time to look once more at Jupiter itself, the great conductor who keeps time for every world that dances around it. The moons of Jupiter do not wander aimlessly. They move in rhythm, a vast invisible symphony conducted by gravity itself. Each orbit, each tug, each subtle acceleration is part of an intricate choreography that has lasted for billions of years. Among all these dancers, 3 stand out for their precision: Io, Europa, and Ganymede. Together they form what astronomers call the Laplace resonance, a gravitational pattern so elegant that it feels less like an accident and more like music written into the fabric of space. In this cosmic arrangement, every time Ganymede completes a single orbit around Jupiter, Europa goes around twice, and Io 4 times. Their orbital periods are locked in a perfect 1:2:4 ratio, a gravitational harmony that keeps the trio eternally connected. Though separated by millions of kilometers, they pull on one another with exquisite timing. When one moon passes a certain point in its orbit, the others are always in just the right positions to exert small repeated tugs. These regular nudges prevent their orbits from becoming perfectly circular. They remain slightly stretched or elliptical, and that slight distortion makes all the difference. For Io, the innermost of the 3, this resonance is both a gift and a curse. The constant gravitational squeezing and releasing as it moves closer to and farther from Jupiter generates immense friction inside the moon, heating it from within. The result is a world of fire, hundreds of volcanoes spewing sulfur and rock into space, powered not by the sun, but by the mathematics of motion. The same gravitational resonance that keeps their orbit stable also fuels Io's eternal restlessness. Europa and Ganymede feel the same rhythm, but their responses are gentler. The stretching they experience generates heat too, though less violently. For Europa, that heat keeps a subsurface ocean liquid beneath its icy shell, a vast sea warmed by invisible tides. In Ganymede's deeper layers, it may help maintain a molten metallic core, giving rise to its magnetic field. In this way, a single gravitational pattern distributes energy across worlds, shaping volcanoes on one moon, oceans on another, and magnetism in a third. It's a celestial energy network powered entirely by motion. The beauty of the Laplace resonance lies in its balance. The moons constantly exchange energy and angular momentum, keeping one another's orbits stable over vast stretches of time. Without this arrangement, Io's orbit might decay, Europa's might drift outward, and Ganymede's rotation might slow. But the resonance locks them into a repeating cycle, where every tug and pull is countered by another. It's a gravitational handshake that keeps the system synchronized, not perfectly still, but perpetually balanced. This kind of resonance isn't rare in the universe, but few examples are as dramatic or as enduring as Jupiter's. The interactions are governed by the same physical laws that make pendulums swing in rhythm, or musical strings vibrate in harmony. Gravity, though invisible, behaves like a spring, one that can store and release energy across unimaginable distances. Each moon's orbit adjusts ever so slightly in response to the others, the way a note bends when played alongside a resonant chord. Over time, these minute adjustments add up to stability, a self-correcting pattern that resists chaos. That stability, however, isn't static. The system breathes, expanding and contracting slightly as energy moves through it. The heat produced inside the moons doesn't come from nothing. It's drawn from their orbital energy. As Io's interior warms and radiates heat into space, its orbit changes by tiny amounts. Those changes ripple outward, and the other moons respond, shifting their own motions to keep the pattern intact. It's an elegant dance of give and take, where gravity acts as both choreographer and timekeeper. This energy exchange is a reminder that even in the depths of space, motion is never truly free. Every orbit carries a cost, every tide a consequence. The heat that glows from Io's volcanoes and Europa's ocean ultimately traces back to the slow, invisible loss of orbital energy, the same way a clock's springs unwind as time moves forward. Gravity here is not only the sculptor of worlds, but their metronome, ticking endlessly, ensuring that the rhythm continues. To picture the resonance, imagine a grand clockwork suspended in space, with gears made of moons and springs made of space-time. Each gear turns at its own pace, yet every rotation affects the next, transmitting motion through gravitational tension. This mechanism doesn't grind or creak. It flows, its motion so smooth that it appears effortless. And yet within that smoothness lies immense power, enough to melt stone, sustain oceans, and shape the magnetic fields of worlds. The Laplace resonance is quite literally the soundless heartbeat of Jupiter's moon system. It's astonishing to realize how enduring this balance has been. Simulations suggest that this resonance may have persisted for billions of years, surviving planetary migrations, impacts, and internal changes. It's a structure that resists both collapse and chaos, perpetually recalibrating itself. Even slight perturbations, a passing asteroid or an evolving orbit, are eventually absorbed into the pattern, the way a clock adjusts its rhythm after a brief jolt. Gravity doesn't simply bind, it organizes, and in organizing it creates. Without resonance, Io would cool and quiet, Europa's ocean might freeze solid, and Ganymede's magnetic heart might fall silent. The very diversity that makes Jupiter's moons so fascinating exists because of this shared rhythm. The Laplace resonance is not just a coincidence of motion, it's the hidden foundation of their individuality. Beyond the physical, there's something poetic about this connection. The same force that pulls tides on Earth and shapes the paths of comets also choreographs this ballet around Jupiter. Gravity, the oldest and simplest of forces, becomes an artist here, weaving patterns from motion, harmony from tension. It reminds us that the universe is not merely a collection of objects, but a web of relationships, each thread tugging gently on the next. If you could stand on any one of these moons and look toward the others, you would see the rhythm made real. Io racing across the sky in days, Europa gliding more slowly, Ganymede slower still, each orbit marking time against Jupiter's eternal spin. The system is a cosmic clock that doesn't count hours, but energy. The flow of heat through stone, ice, and metal. This is the quiet genius of Jupiter's realm. Chaos tamed by resonance, heat born of gravity's rhythm, time measured in tides. A system that endures not because it avoids tension, but because it embraces it, turning stress into motion, and motion into warmth. And beyond those carefully balanced moons, the planet itself continues to hum with energy. Storms swirling above, particles racing within its magnetic field, a giant machine of motion and heat. The clockwork of gravity gives way now to turbulence and light, to the restless energies that make Jupiter itself alive. Jupiter glows with a warmth that does not come from the sun. Though it lies more than 700 million kilometers from our star, the giant planet shines faintly in infrared, radiating nearly twice as much energy as it receives. In a solar system where most worlds rely on sunlight for heat, Jupiter makes its own. It is a planet that has never quite cooled off, still shedding the energy it was born with, billions of years after its formation. That internal heat defines almost everything about Jupiter's atmosphere. Deep within, the planet's interior remains hot from gravitational compression, the slow squeeze of hydrogen and helium under the weight of the world itself. As the planet contracts ever so slightly over time, it converts gravitational potential energy into thermal energy, warming the gases from within. Some scientists describe this process as Kelvin-Helmholtz contraction, but in simpler terms, Jupiter is still settling into itself, radiating the warmth of an unfinished birth. This slow leak of heat rises upward, escaping through layers of gas and cloud. It fuels convection, the same process that drives boiling water on a stove, but on a scale so vast that entire continents could fit within a single convective cell. Warm gas from the planet's depths rises, cools, and sinks again in enormous cycles, churning the atmosphere and feeding the planet's endless weather. These vertical motions carry energy through the layers, forming the belts and zones that stripe Jupiter's surface, the ovals and vortices that dance between them, and the towering storms that flash with lightning deep in the clouds. Because Jupiter's internal heat is so strong, it dominates over sunlight in driving the weather. Even though the planet receives only 4% of the sunlight that Earth does, its atmosphere remains restless and dynamic. The sun's contribution is little more than decoration. It paints subtle differences in temperature between equator and pole, but doesn't set the rhythm. On Jupiter, the heat comes from below, not above. It's a world that quite literally makes its own cozy. That warmth, however, doesn't distribute itself evenly. Rising gas creates the pale, high-pressure zones, while sinking gas forms the darker belts, each a band of different temperature and chemistry. Between them, jet streams sweep around the planet, transporting energy from place to place. The circulation is so vast and stable that many of the patterns have persisted for centuries. The Great Red Spot, for example, may owe its longevity to this deep internal heat, a steady flow of energy that keeps the atmosphere churning from the bottom up. Despite its storms, Jupiter's weather has a kind of long-term consistency. It doesn't experience seasons like Earth or Mars because its axis is tilted only about 3 degrees relative to its orbit. That means the sunlight it receives hardly changes throughout the year. No summer, no winter, no spring. Just a continuous, slow rotation under a nearly constant sun. The lack of seasonal forcing allows large-scale patterns to persist for decades or even centuries without major interruption. Yet, the atmosphere is anything but static. Beneath the familiar stripes and ovals, Jupiter is full of subtle rhythms and sudden surprises. Every so often, new storms appear from the depths, bright white plumes rising through the darker belts, expanding over weeks into enormous planet-spanning disturbances. These outbursts can rearrange entire regions of cloud, altering the colours and banding that astronomers have tracked for centuries. In the 1930s, observers watched a huge eruption in the south equatorial belt, and in more recent years, spacecraft have recorded smaller but equally fascinating convective events. Jupiter's weather may seem steady, but it breathes in slow cycles, calm for years, then suddenly eruptive, as if the planet occasionally adjusts its atmospheric balance before returning to its familiar stripes. The consistency of Jupiter's climate doesn't mean it's simple. Beneath the visible clouds, the atmosphere continues downward for thousands of kilometers, transitioning from gas to liquid, from turbulence to calm, and finally into the metallic hydrogen layer where the planet's magnetic field begins. Heat from the interior percolates upward through this enormous column, changing character along the way. In the deeper regions, convection dominates. Giant plumes of warm hydrogen rise and cool, releasing energy as they go. Higher up, where pressures are lower, the motion becomes more chaotic, creating waves, eddies, and the intricate filamentary structures seen in spacecraft images. Lightning is another expression of this internal energy. Most flashes occur in the water cloud layer, far below the upper ammonia haze, where convection is strongest. Here, warm updrafts and cool downdrafts create static charge separations, much like on Earth, but on a grander scale. The bolts that flash across Jupiter's night side are immense, some hundreds of times more powerful than a typical terrestrial lightning strike. Each one illuminates the surrounding clouds, momentarily revealing the complex structure of the storms within. These flashes are Jupiter's heartbeat, proof that the planet's energy is constantly on the move. The upper atmosphere too reflects this dynamic energy balance. It glows faintly in infrared, radiating away the heat rising from below. Interestingly, measurements have shown that Jupiter's upper layers are much warmer than they should be, given their distance from the Sun. This energy excess likely comes from the same internal processes, the heat leaking upward from deep within, along with the energy input from auroral activity driven by the magnetic field. Even here, far above the cloud tops, Jupiter remains self-sustaining, its warmth spread by the combined action of gravity, magnetism, and convection. If you could stand at the edge of the atmosphere and watch this energy move, you'd see it as a kind of slow shimmer, waves and eddies rippling through the gas, transferring heat, momentum, and chemistry between layers. The planet's weather is not a random collection of storms, but a connected system, shaped by physics and fueled by persistence. The same heat that once formed the planet still circulates within it, ensuring that Jupiter never truly rests. The balance between internal and external energy makes Jupiter both predictable and surprising. Its average temperature changes little from year to year, yet its storms are capable of explosive growth. It radiates the same heat today that it did when the dinosaurs walked the Earth, yet the patterns of its atmosphere remain in flux. To study Jupiter is to study stability through motion, a lesson in how energy can find equilibrium not by stopping but by flowing continuously. In a way, Jupiter is a world-sized hearth, one that has been burning slowly since the dawn of the solar system. It glows not because of light from the sun, but because of its own enduring warmth, its own gravitational memory. Every storm, every lightning flash, every convective plume is part of that ancient fire expressing itself through gas and cloud. And as we marvel at this restless balance, we remember that much of what we know about it comes from the eyes and instruments we've sent there. Machines built on Earth, hurled across space to listen to Jupiter's winds, measure its gravity, and trace its invisible heat. The next chapter in the planet's story belongs to them, the explorers that have watched the giant breathe and learned to read its storms. For centuries, Jupiter was a mystery seen only through lenses, a distant orb of stripes and storms gliding silently across the night sky. Then, in the 20th century, humanity decided to pay the king of planets a visit. One by one, our mechanical messengers set sail across the void, bearing questions instead of tribute. They travelled for years, braving cold and radiation, to look closely at a world so immense that even sunlight takes nearly an hour to reach it. The first to arrive were the pioneers, small, robust scouts built for discovery. Pioneer 10 flew past Jupiter in 1973, becoming the first spacecraft to cross the asteroid belt and the first to encounter the giant planet up close. Its twin, Pioneer 11, followed the next year. These early explorers were simple by modern standards. Their computers had less memory than a pocket calculator, but their courage was unmatched. As they approached Jupiter, they entered a realm saturated with radiation powerful enough to fry electronics. Their instruments trembled under the onslaught, yet they endured long enough to send back the first direct measurements of the planet's magnetic field, radiation belts, and atmosphere. For the first time, Jupiter was no longer a distant point of light, but a physical place. The pioneers' findings astonished scientists. They revealed a magnetic field so strong it filled a volume of space larger than the sun itself, and radiation belts more intense than anyone expected. They detected the enormous bull shock where the solar wind crashes into Jupiter's magnetosphere, and confirmed that the planet emits far more heat than it receives. Pioneer 11 even took humanity's first close-up images of the Great Red Spot, glimpsing its swirling complexity from just over 40,000 kilometers away. Those fuzzy, grainy photos were the opening lines in Jupiter's modern story. Then came the Voyagers. Launched in 1977, Voyager 1 and Voyager 2 were the great surveyors of the solar system, the first grand tourists of the outer planets. When they reached Jupiter in 1979, the view was breathtaking. Their cameras revealed the planet in vivid colour, roiling clouds, turbulent belts, and delicate patterns of motion that changed from hour to hour. They captured lightning flashes in the night, auroras near the poles, and swirling eddies surrounding the Great Red Spot. The images transformed Jupiter from a distant idea into a living world. But the real shock came from its moons. Voyager's flybys uncovered volcanic plumes erupting on Io, ice fractures on Europa, and grooved terrains on Ganymede. It was as if a whole miniature solar system had been hiding in plain sight. For the first time, scientists began to see Jupiter not as a single planet, but as a vast ecosystem of worlds, each shaped by its parent's gravity and magnetism. Voyager 2 continued on, giving us stereo views of the atmosphere and revealing new details in the ring system. Thin, dusty, and faintly glowing. The missions together taught us that Jupiter was more than a ball of gas. It was dynamic, layered, and endlessly complex, with weather patterns stretching thousands of kilometers deep. By the time the voyagers left, bound for Saturn and beyond, humanity's relationship with Jupiter had changed forever. In the years that followed, other visitors paused to admire the giant on their way elsewhere. Cassini, bound for Saturn, flew past in 2000 and took exquisite images of Jupiter's cloud tops, capturing fine-scale structures in swirling colour. The New Horizons spacecraft heading to Pluto also swung by in 2007, using Jupiter's gravity to accelerate toward the outer edge of the solar system. Each of these encounters added small but valuable pieces to the puzzle, brief glances that refined our maps and improved our understanding of the planet's immense energy and magnetism. But one mission dared to stay. In 1995, the Galileo spacecraft arrived after a 6-year journey and became the first to orbit Jupiter. Named for the man who had first spotted its moons through a telescope in 1610, Galileo was a brave but ill-fated explorer. A technical failure kept its main antenna from opening fully, forcing engineers to use a backup system to transmit data slowly, like sending postcards through a straw. Despite the challenge, Galileo accomplished more than anyone dared hope. It dropped a small probe directly into Jupiter's atmosphere, a 1-hour plunge through layers of cloud and storm before the crushing pressure silenced it. That descent gave us our first direct glimpse of Jupiter's weather. The thickness of its clouds, the distribution of its elements, the surprising dryness of the air in certain regions. Meanwhile, the orbiter studied the planet and its moons for years, revealing details of their magnetic fields, internal structures, and even hints of subsurface oceans. It watched lightning storms rage across the night side, mapped volcanic eruptions on Io, and detected the strong possibility of liquid water beneath Europa's ice. After 14 years in space, Galileo's mission ended in 2003 when it was deliberately guided into Jupiter's atmosphere, not as an act of destruction, but as protection. Scientists didn't want the aging spacecraft to accidentally crash into Europa, where it might contaminate a potentially habitable world. So, in its final moments, Galileo became part of the planet it had studied so faithfully. Then, more than a decade later, a new messenger arrived, one designed specifically to unravel Jupiter's deepest mysteries. Juno, launched in 2011 and arriving in 2016, entered a highly elliptical polar orbit, looping from pole to pole every 53 days. Unlike previous missions that skimmed around the equator, Juno looked down from above, giving us our first views of the poles, regions of swirling chaotic storms unlike anything seen elsewhere in the solar system. Its trajectory kept it safe from the worst of Jupiter's radiation, darting in close for quick, intense measurements before retreating again into calmer space. Juno carried instruments unlike any before. Its gravity science experiment measured tiny changes in the spacecraft's motion, allowing scientists to map how masses distributed within the planet, clues to the structure of its core. Its microwave radiometer peered deep beneath the clouds, revealing the layers of ammonia, water, and hydrogen gas that make up Jupiter's weather system. The magnetometer mapped the planet's magnetic field in exquisite detail, showing that it is far more complex and lopsided than expected. Not a simple dipole, but a swirling patchwork of magnetic regions, especially strong near the equator. Perhaps the most surprising discovery was the nature of Jupiter's interior. Juno's data suggested that the planet may not have a distinct solid core at all, but a fuzzy one, a region where rock, ice, and hydrogen mix gradually together rather than forming sharp boundaries. This challenged long-held assumptions about how giant planets form. Other surprises followed. Unexpected concentrations of ammonia in some regions, suggesting deep atmospheric currents that move material unevenly, and an interior circulation that extends thousands of kilometers below the visible clouds. Jupiter, it turned out, is far less uniform than it appears. Through Juno's instruments, we've also learned that the polar regions host clusters of cyclones, vast, geometrically arranged storms that seem to maintain perfect spacing, as if choreographed by some invisible force. The poles themselves are wild and beautiful, swirling with blues, greens, and pearly whites. They look almost like works of abstract art, painted by wind and time. For all their technical brilliance, these spacecraft are, at heart, extensions of curiosity, machines built by human hands to stand in the radiation and cold where no person ever could. They've endured conditions that would destroy nearly anything else, transmitting knowledge bit by bit through the blackness of space. There's something humbling about that. Silent explorers orbiting a planet of storms, listening to lightning and magnetism, translating chaos into understanding. As Juno continues to send back data, its mission reminds us that exploration is never truly finished. Each discovery raises new questions about Jupiter's origins, its structure, and the stories it still holds in its swirling depths. And sometimes, even as we study the giant on our own terms, it reminds us that not every visitor arrives by invitation. Jupiter's gravitational reach extends far beyond its clouds, and every so often something unplanned wanders too close to the king. In July of 1994, Jupiter became the stage for one of the most dramatic astronomical events ever witnessed. A comet named Shoemaker-Levy 9, once a single body, had been torn apart by Jupiter's gravity the year before. Its fragments, more than 20 pieces, each several kilometers wide, lined up like glowing beads and plunged into the planet one after another. For a week, the world watched as these icy remnants slammed into the giant, creating fireballs that rose higher than the planet's limb and scars larger than the Earth itself. It was a celestial collision, both terrifying and beautiful, and it reminded humanity that the solar system is not a quiet place. When those fragments struck, they didn't hit a solid surface. Jupiter has none, but rather dove into layers of gas, compressing and heating them until they exploded in bursts of light and energy. Each impact released more energy than millions of nuclear bombs. Telescopes on Earth saw plumes rise thousands of kilometers into the atmosphere, followed by dark marks that spread and drifted with the planet's winds. These bruises lingered for months, smudges of carbon and dust swirling in the endless flow of Jupiter's clouds. It was as if the planet itself had absorbed the blows and carried the memory on its skin. For scientists, those scars were not just dramatic, they were revealing. By studying the impact sites, astronomers could learn how Jupiter's atmosphere behaves under extreme conditions. The plumes exposed deep layers of gas that are usually hidden from view, offering insights into temperature, composition, and cloud dynamics. The way the scars evolved over time helped refine models of how energy moves through the atmosphere, how winds circulate, and how debris disperses. Shoemaker-Levy 9 was, in effect, an accidental experiment, one no scientist could have dared to plan, but one that taught us more about Jupiter in a week than decades of quiet observation. It also reminded us of Jupiter's gravitational might. The same force that captured the comet and tore it apart is the same that shapes the orbits of countless asteroids and comets across the solar system. Jupiter acts like a cosmic gatekeeper, its immense gravity influencing the paths of objects that stray too close to the Sun. Some are flung outward into distant orbits, while others are pulled inward, sometimes toward Earth. This has led to the popular idea of Jupiter as the solar system's great protector, a planetary shield that intercepts or deflects dangerous comets before they can threaten the inner worlds. There's truth to that image, but also nuance. Jupiter certainly captures and absorbs its share of wandering debris. Its huge cross-section and deep gravity well make it an effective sink for comets and asteroids. but that same gravitational reach can also act as a slingshot, redirecting some bodies toward the inner solar system instead of away from it. In this sense, Jupiter is both guardian and gambler, a planet that sometimes saves, sometimes risks, and always plays by gravity's rules. The very same force that pulled Shoemaker Levy 9 into destruction could, under different circumstances, send another comet Earth's way. Jupiter doesn't choose sides, it simply balances the celestial books. Since that spectacular week in 1994, astronomers have continued to watch Jupiter for similar impacts, and the planet has not disappointed. In 2009, an Australian amateur astronomer spotted a new dark scar near the South Pole, evidence of another large object colliding with the giant. Smaller flashes have been detected since then, caught by both professional observatories and backyard telescopes. These brief, bright bursts, often lasting only seconds, are thought to be meteoroids or small asteroids burning up in the upper atmosphere. Jupiter, it seems, continues to collect the wandering remnants of the solar system, sometimes quietly, sometimes dramatically. Each impact, large or small, teaches us something new. The brightness of the flash reveals the speed and size of the incoming body. The chemical signatures in the aftermath tell us what the object was made of: ice, rock, or a combination of both. The way the atmosphere responds gives clues about its density, its layers, and the depth at which the energy dissipates. In essence, every strike is a natural probe, a violent but invaluable form of exploration. These collisions also help scientists refine our understanding of planetary defense. By studying Jupiter's encounters, we learn how comets fragment under tidal stress, how debris behaves after impact, and how shock waves spread through thick atmospheres. The lessons scale upward and downward alike, from gas giants to terrestrial worlds. What happens on Jupiter can inform how we model impacts on Earth, how they release energy, distribute dust, and alter climate. Even in chaos there is education. From another perspective, Jupiter's role as both shield and scatterer has broader consequences for the architecture of the solar system itself. Its gravity has shaped the orbits of countless small bodies, clearing the region between Mars and itself to create the asteroid belt and influencing the paths of comets in the distant Kuiper belt. Without Jupiter, the inner planets might have faced far more frequent bombardments in their early histories. The Earth, for all its life and oceans, may owe some of its stability, and perhaps even its habitability, to the presence of the giant next door. There's something strangely elegant about this balance. Jupiter is the solar system's enforcer and historian all at once. Every impact mark is a note in the planet's long record of encounters, written in fleeting ink across its clouds. They fade within months or years, erased by the winds, but for a time they tell the story of an ancient process still at work, gravity's endless habit of reshaping, redirecting, and reminding. Shoemaker Levy 9 was a rare spectacle, but it was also a humbling one. Watching those fragments fall, scientists and observers alike felt a deep sense of awe at both the fragility and the order of the cosmos. The event showed us how the same forces that form planets can also destroy them, and how even in destruction, the universe reveals itself with clarity. Jupiter bore the scars, but the lesson belonged to us. If you were to look at Jupiter now, you'd see no trace of those dark marks. The winds have swept them away, and the planet has returned to its usual tapestry of creams and ochres. Yet somewhere beneath the clouds, the traces still exist in memory. Chemical residues, temperature gradients, subtle imprints in motion. In that sense, the planet itself remembers, even if our eyes cannot see it. Every world bears scars, but Jupiter's are written in gas, temporary, shifting, yet profound. They remind us that the solar system is still alive, still sculpting itself, still carrying forward the same interplay of gravity and motion that began billions of years ago. These encounters are not just accidents, they are conversations between worlds and wanderers, each impact a punctuation mark in the long sentence of time. And as we step back from Jupiter's banded surface and its fleeting bruises, a larger picture comes into view. The lessons it offers about gravity, formation, and resilience extend far beyond its own orbit. In studying Jupiter, we glimpse not just the heart of our own solar system, but the nature of planets everywhere. Jupiter is not alone. Across the galaxy, telescopes have uncovered thousands of planets that echo its form, worlds of gas and cloud, immense and mysterious circling distant suns. Some are far larger, some smaller, some searingly hot, and some adrift in the cold. Each one adds a new note to the cosmic symphony of worlds, a variation on the theme that Jupiter first introduced. And yet, in this growing orchestra of planets, our own giant remains the archetype, the first gas giant we ever knew, and still the key that helps unlock the stories of all the others. When astronomers began discovering exoplanets in the 1990s, they expected to find systems much like our own, rocky worlds near their stars, giants far away. Instead, the universe surprised them. The first worlds to reveal themselves were hot Jupiters, enormous gas giants orbiting astonishingly close to their stars, sometimes completing an orbit in just a few days. These planets, like 51 Pegasi b, defied all expectations. They were bloated by heat, tidally locked so that one side faced eternal day, while the other remained in night, their atmospheres whipped by supersonic winds and glowing faintly from their own warmth. At first, scientists thought these exotic worlds might be rare oddities, but as more discoveries followed, it became clear they were common. They challenged every assumption about how planets form. In our solar system, Jupiter orbits far from the Sun, in a region cool enough for ice to condense, the frost line. There, solid grains of ice and rock accumulated into a massive core that could capture vast amounts of gas. Close to a star, such materials would have evaporated before they could form anything substantial. So how could hot Jupiters exist? The answer, it seemed, was motion. The leading theory is that many of these giants didn't form where we see them now. They were born farther out, like Jupiter, and later migrated inward through interactions with the surrounding disk of gas and dust, or through gravitational encounters with other planets. This migration reshaped their systems, pushing smaller worlds aside or swallowing them altogether. Some hot Jupiters may have even fallen into their stars after spiraling too close. It's a violent form of choreography, one that shows how dynamic young planetary systems can be. But not all exoplanetary giants ended up so near their suns. Between the extremes of hot Jupiters and cold, distant giants lie the warm Jupiters and mini Neptunes, planets that bridge the gap between gas and rock, often with thick atmospheres and complex layers of cloud. Some are roughly the size of Neptune, others as massive as Saturn. Their diversity tells us that planetary formation is not a single process, but a spectrum of outcomes. A small change in initial conditions, a little more gas here, a little less dust there, can lead to wildly different results. By comparing these worlds to Jupiter, scientists can test how universal its story might be. Did all giant planets begin with a solid core that grew large enough to attract gas? Or did some form rapidly, collapsing directly from the disk's material in a kind of miniature star formation? Jupiter itself may hold the answer, its fuzzy core a clue that both processes could have played a role. The patterns we see elsewhere suggest that Jupiter's birth was not a one-off miracle, but one version of a common cosmic theme. Jupiter also provides context for understanding habitability. Its immense gravity and early migration, or lack thereof, likely shaped the distribution of material in our solar system. By holding the outer regions stable and scattering dangerous debris, it may have helped Earth remain safe enough for life to flourish. In other systems, the presence or absence of Jupiter-like planets can determine whether smaller Earth-like worlds survive or perish. Too much migration, and the inner regions become chaos. Too little, and the system may never form rocky planets at all. In that sense, Jupiter is not just a planet, but a sculptor of worlds. Its influence extends beyond its own orbit, defining the potential for life across the solar system. Even today, as astronomers map thousands of distant systems, they find echoes of this relationship. Some stars host giants far from the habitable zone. Others have chains of smaller gas planets locked in resonances that recall Jupiter's dance with its moons. There are systems with multiple giants in eccentric orbits, where each world's gravity keeps the others on edge, and systems with none at all, where rocky planets reign undisturbed. In every case, the giants are the architects, setting the tone for everything around them. The variety is astonishing. Some exoplanetary Jupiters are so close to their stars that their atmospheres boil off into space, forming glowing tails of gas like comets. Others orbit far in the dark, with temperatures hundreds of degrees below freezing. A few wander between stars entirely, cast adrift by gravitational encounters, roaming the galaxy as planetary nomads. Each one offers a different answer to the question of what it means to be a giant planet. And yet, amidst all this diversity, Jupiter's presence feels strangely central, a reference point against which all others are measured. Its structure, its storms, its magnetic field, its moons, these have become the yardstick for understanding gas giants everywhere. When astronomers detect faint light curves from a distant world, they often describe its winds, clouds, or chemistry in Jupiter units. It has become not just a planet, but standard of comparison, the original note from which all harmonies of giant worlds are tuned. The more we learn, the more we see that Jupiter's story is both universal and unique. It follows the rules of planetary physics, but plays them with its own rhythm. Its relatively mild migration may have been the key that preserved the stability of the inner solar system, a delicate balance that allowed Earth to remain calm while chaos reigned elsewhere. Many systems, by contrast, appear to have sacrificed their inner worlds when their own giants wandered inward. Jupiter's restraint, in a sense, is the reason we can look out at the stars and study other Jupiters at all. There's a quiet poetry in that. The idea that our planet's protector might also be our interpreter, teaching us how the universe builds and rebuilds itself. Every exoplanet discovery, from the blazing hot Jupiters to the frozen giants beyond their star's light, adds another verse to that same song. The melody is familiar, but the tempo changes with every system, each variation playing on a theme that began right here, circling in the dark beyond Mars. If the galaxy were a vast symphony, Jupiter's note would be deep and resonant, a fundamental tone from which other worlds take their pitch. We can now hear that chord echoing everywhere, in the close-in giants that blaze like lanterns, in the distant wanderers that glide in the dark, in the layered skies of mini-Neptunes painted with vapour and haze. 1,000 variations, all drawn from the same deep pattern of gravity, gas and light. And as we listen to those echoes, we find ourselves nearing the calm at the edge of understanding, a place where knowledge fades gently into wonder, and where Jupiter, the king of planets, continues to whisper the music of creation. In the great gallery of the solar system, Jupiter stands as both a masterpiece and a mystery, a world where chaos and order are not enemies but dance partners. Everything about it is an act of balance, storms that never end yet remain contained, winds that rage but create structure, a planet born from disorder that now holds harmony and motion. To understand Jupiter is to see how the universe sculpts beauty from turbulence, not by erasing it, but by shaping it into rhythm. From the earliest dust of the protoplanetary disk, Jupiter rose first. Its birth shaped everything that followed, sweeping clean, rearranging, protecting, and defining. Out of the chaos of gas and rock, it gathered itself, capturing enough material to become a world so massive that it still glows with leftover heat from its creation. That same heat keeps its atmosphere alive today, feeding storms and circulation that have endured for centuries. In the quiet of its gravity, it became the conductor of the solar system's orchestra, setting the pace for planets, asteroids, and comets alike. Its colours, creams, golds, rusts, and ochres, are the visible trace of chemistry and sunlight working together. Ammonia, sulfur, water, and trace elements mix and swirl in layered clouds, their hues shifting with altitude, temperature, and time. Those stripes that stretch around the planet aren't decoration. They're the product of jet streams flowing in alternating directions, the result of rotation so rapid that the day lasts less than 10 hours. From those bands rise storms as large as worlds, some new and bright, others ancient and enduring. The great red spot, vast enough to swallow Earth, has spun for centuries, fading and reshaping, yet never losing its presence. Beneath the storms, the planet deepens into mystery. Hydrogen, the lightest element, is pressed under unimaginable weight until it behaves like metal, conducting electricity and generating a magnetic field so powerful it stretches millions of kilometers into space. That invisible magnetosphere traps particles, sparks auroras, and hums with energy, a magnetic song resonating through the void. It's one of the strongest in the solar system, a reminder that even invisible forces can shape the fates of worlds, and orbiting within that field is a miniature system of its own. Dozens of moons, each with its own story. Io, restless and volcanic, forever reshaped by Jupiter's pull. Europa, the quiet ocean world, hiding saltwater seas beneath its ice. Ganymede, the magnetic moon with an iron heart that echoes its parents. Callisto, the archivist of ancient impacts, a frozen time capsule of the solar system's earliest days. Together, they make Jupiter not just a planet but an ecosystem, a cosmic family bound by gravity and rhythm. Even the way those moons move speaks to order rising from chaos. Their orbits are locked in resonance, tugging at one another in a steady gravitational dance that keeps them warm and alive inside. Every pull, every stretch, every subtle oscillation transfers energy through their crusts and cores. It's a quiet conversation, measured in tides and time, a gravitational heartbeat that has pulsed for billions of years. Through the eyes of our spacecraft, we've learned to listen to that heartbeat. The pioneers, the Voyagers, Galileo and Juno, each one a messenger braving radiation, distance and time to bring home stories of wind, magnetism and motion. They showed us that Jupiter is not static, not simple and not uniform. It is layered, dynamic and filled with surprises. Ammonia rising in plumes, lightning flashing deep below, a fuzzy core blurring the line between rock and gas, all tell us that even the mightiest of worlds remains a work in progress. And sometimes the universe itself sends its own messages. The fragments of Shoemaker-Levy 9, falling one by one into Jupiter's atmosphere, left scars that faded but never truly vanished from memory. Those dark marks reminded us of how gravity binds and breaks, how creation and destruction share the same physics. They also revealed Jupiter's double role, protector and provocateur, shield and scatterer. The same gravity that swallows comets also flings them across the cosmos, a force of balance rather than preference. Beyond our solar system, Jupiter's reflection appears again and again, in hot Jupiters circling close to alien suns, in cold giants orbiting far in the dark, and in warm, misty worlds that lie between. Each is a variation on the same theme: gravity gathering, heat stirring, order emerging. The story of Jupiter, written in hydrogen and helium, repeats across the galaxy in 1,000 different ways. It's the pattern that connects us to distant stars, a universal design of motion, magnetism, and patience. Through all of this, Jupiter remains a lesson in scale and time. Its storms are centuries long, its magnetosphere extends beyond imagination, its gravity has shaped the fates of worlds. To gaze at it is to feel small, but not insignificant, to be reminded that complexity and calm can coexist. In its endless winds, we see the same processes that formed galaxies and atoms alike: energy seeking balance, chaos settling into rhythm, and perhaps that is Jupiter's greatest gift: perspective. It teaches that order and turbulence are not opposites, but partners in creation. Without motion, there is no pattern. Without energy, no calm. Even chaos, given time, can become something structured and serene. The planet is not a symbol of dominion or violence, but of endurance, of a system that finds harmony not by resisting disorder, but by weaving it into something magnificent. For all its grandeur, Jupiter rules gently. It does not command through destruction or conquest, but through balance. It's the only king in the solar system whose crown is made of clouds and whose power comes from wind. There's humour in that. The most powerful planet of all governs through motion, not stillness, through the calm persistence of physics rather than the drama of flame. And as we leave Jupiter behind, its belts and bands, its moons and magnetism, its storms and silence, we can take with us a kind of peace. The knowledge that beauty is not the absence of chaos, but its transformation. That even in the most violent systems, patterns emerge. That the universe does not rush toward perfection, but toward balance. When chaos becomes order, it becomes a world, and for a while, it becomes home for the eyes and mind. Thank you for drifting through this journey tonight. May Jupiter's calm vastness follow you into rest, and may your thoughts, like the planet's clouds, find their quiet rhythm as you drift towards sleep. The stars will keep watch, the storms will keep spinning, and all will remain in motion, softly, endlessly, beautifully,